Hello there, and welcome to Physics with William, where curiosity gets comfortable, the universe slows down a little, and science takes the long, quiet road toward rest. Tonight, we are settling into one of the deepest questions modern physics has ever asked, a question so simple on the surface that it almost sounds like something a child might ask while looking out of a bedroom window. What is space-time really made of? Not space by itself, not time by itself, but space-time, that strange combined thing that holds every star, every planet, every drifting speck of dust, every falling apple, every passing thought, and every sleepy listener tucked beneath a blanket somewhere on Earth. It is the stage on which everything happens, but it may not be a stage in the ordinary sense. It bends, it stretches, it ripples, it responds when matter moves through it. It seems smooth when we look at the night sky, yet some physicists suspect that if we could look closely enough, far more closely than any microscope could ever manage, we might find that space-time has a hidden structure, a kind of deeper grain. That is a very odd idea. We usually think of space as emptiness, the room around you, the air above your head, the distance between your hand and the nearest wall, the vast darkness between Earth and the Moon. Space feels like the absence of things. It is where objects are, not an object itself. Time feels different, but just as familiar. It is what clocks measure. It is what makes morning become afternoon, what lets soup cool on the table, what turns a plan into a memory. Time feels like something that passes, although no one has ever caught a piece of it in a jar. And yet, according to modern physics, space and time are not separate backgrounds. They're woven together into one physical structure. That structure can change, and because it can change, we're allowed to ask what it is made of. So before we wander further into that question, let me ask you something simple. Where are you listening from tonight, and what does the space around you feel like right now? Are you in a quiet room with the lights low? Are you near a window, with a little dark sky pressing gently against the glass? Is it late where you are, with the world outside settling down, or are you listening from a different time zone where the day is only beginning? I always find that thought comforting during a topic like this. Somewhere, someone is hearing these words in the middle of the night. Somewhere else, someone is hearing them in morning light. Different clocks, different skies, different places on the same turning Earth, all resting inside the same vast fabric of space-time. If you find this kind of journey soothing, if the slow unfolding of science helps your mind soften after a long day, I would be very grateful if you gave the video a like, subscribed, or simply stayed a while. It helps this calm little corner of the internet reach other people who may also enjoy drifting through the universe without needing to race toward an answer. And tonight, racing would be very inappropriate. Space-time has been around for quite a while. It can wait for us to understand it gently. Now, when we ask what space-time is made of, we have to be careful. It is not like asking what a chair is made of. A chair might be made of wood, metal, fabric, or plastic. We can cut into it, sand it down, smell the sawdust, or complain that one leg is slightly shorter than the others. It's also not like asking what water is made of, because there we can talk about tiny particles, molecules, and atoms. We can say that water has parts, and those parts have smaller parts, and physics can follow them down into a busy little world of charges and forces. But space-time is stranger than that. It is the thing in which cutting, measuring, moving, and comparing all seem to happen. Trying to ask what space-time is made of is a little like trying to inspect the ruler you use to inspect every other ruler. You can do it, but eventually things become delicate. For most of everyday life, we do not notice space-time at all. You put a cup down on a table, and it stays where it is unless a cat becomes involved. You walk across a room, and the room does not appear to stretch like warm toffee. You wait for a kettle to boil, and time does not suddenly run sideways into the cupboard. Our senses are built for ordinary scales, ordinary speeds, and ordinary gravity. To us, space seems stable and time seems steady. That is because in daily life, space-time behaves politely. It lets us make tea, keep appointments, and misplace our keys with reliable consistency. But the universe is not required to behave according to our household expectations. When we look at extreme situations, near massive stars, around black holes, across the expanding universe, or deep into the quantum world, the familiar picture begins to loosen. Space is not just a container. Time is not just a clock reading. The two are linked, and their linking is not decorative. It matters. The path a planet follows around the sun, the way light bends near a galaxy, the tiny corrections needed for satellites to guide your phone, all of these depend on spacetime being something active. This is already enough to make spacetime feel almost material. If something can bend, stretch, ripple, and affect the motion of matter, then surely it must be something. But what kind of something? That is where the question becomes difficult, and also wonderfully interesting. A wave in the ocean is made of water. A ripple in a sheet is made of fabric. A sound wave is made of air or some other medium vibrating. So when scientists detect ripples in space-time called gravitational waves, it is tempting to ask what is doing the rippling. Is space-time a substance? Is it a field? Is it geometry? Is it information? Is it something that only appears smooth because we are too large and slow to see its deeper structure? The safest answer is that we do not yet know in a final way. Science has learned a great deal about how space-time behaves, but knowing how something behaves is not always the same as knowing what it is made of. You can learn how a clock ticks without knowing how every gear was made. You can learn how a river flows without knowing the shape of every stone beneath it. In the same way, physics has powerful descriptions of space-time, especially through Einstein's theory of gravity. But at the deepest level, the question remains open. That openness is not a failure. It is one of the most honest and interesting places in science. A good mystery is not just a gap in knowledge, it is a signpost. It points toward the edge of the map and says, very quietly, there may be more here. For a long time, people treated space and time as a kind of background. They were the setting, not the main character. Imagine a play in a theatre. The actors move across the stage, speak their lines, drop props, fall in love, start arguments, and occasionally exit through the wrong door. The stage is there, solid and unmoving. It does not care what the actors do. In the older view of physics, space and time were like that stage. Objects moved through space. Events happened in time. Space and time themselves simply existed in the background, calm, silent, and rather underappreciated. Then Einstein changed the role of the stage. In his picture, space-time is not a passive flaw beneath the drama. It participates. Matter and energy shape it. Its shape tells matter how to move. Gravity is not simply a pull in this view. It is the result of curved space-time guiding the paths of objects. The Earth goes around the Sun not because an invisible rope is tugging it, but because the Sun changes the geometry around it, and Earth follows the natural path through that geometry. That sounds less like a stage and more like a dance floor that slopes, dips, and subtly directs every step. This does not mean space is a rubber sheet, although that image is often used because it is easy to picture. The rubber sheet picture is helpful for a moment, but it can also mislead us. Space-time is not a physical fabric floating inside some larger room. It is not a blanket stretched across the universe with stars sitting on top of it like heavy marbles. The universe does not need another outside space to contain its space-time. Space-time is the arena itself. The bending is not happening into some hidden extra room we can easily imagine. It is a change in the relationships between distances, durations, paths, and events. That may sound a little slippery, so let us bring it back down to earth. If you have ever used a map, you already know that geometry matters. A flat paper map can show roads, rivers, and cities, but the earth itself is curved. If you travel far enough, the flat map becomes a compromise. Lines that look simple may not reflect the true shortest path on a globe. Airplanes often take routes that look curved on a flat map, because they are following something closer to the shortest path over the curved surface of Earth. Geometry changes what counts as straight. In general relativity, gravity is partly a story about what counts as straight in space-time. A falling object is not necessarily being pulled away from its natural motion. It may be following the straightest possible path available through curved space-time. That idea is not easy to feel in your bones, because our everyday instincts were not built by studying distant galaxies. They were built by walking, reaching, balancing, and trying not to trip over things in dim hallways. Still, the mathematics and the observations agree with astonishing precision. Space-time curves, and that curvature has consequences. Yet even this successful picture leaves a deeper question waiting quietly in the corner. If space-time can curve, what gives it the ability to curve? If it can ripple, what is the ripple made from? If it can expand with the universe, what is expanding? These are not easy questions. They lead us toward the border between gravity and quantum physics, which is one of the great unfinished conversations in modern science. Quantum physics describes the small world with remarkable success. It tells us that particles are not tiny billiard balls in the simple old sense. They are excitations of fields, patterns of possibility, events that do not always fit neatly into everyday pictures. According to modern physics, what we call empty space is not truly empty. It is filled with fields, and those fields can fluctuate. Particles can appear as disturbances in them. Even in the quietest vacuum there is activity at the quantum level. Empty space is not nothing. It is more like a very low whisper rather than absolute silence. So here is where the puzzle deepens. General relativity treats space-time as smooth geometry. Quantum physics treats the contents of the universe as fields and probabilities. Each works beautifully in its own domain. But when we try to describe situations where both must matter at once, such as the centre of a black hole or the first moments of the universe, our current theories no longer fit together cleanly. It is a bit like having two excellent maps printed at different scales, one for continents and one for city streets, and discovering that at a certain border the roads no longer line up. This mismatch has led physicists to suspect that space-time may not be fundamental. That is a careful word. Fundamental means something that is not made from something deeper. If space-time is not fundamental, then it may be more like temperature. Temperature feels real. A warm cup of tea is clearly different from a cold one, especially when you are looking forward to drinking it. But temperature is not a substance hidden inside the tea. It emerges from the motion and behaviour of many tiny particles. It is a large-scale property, useful and real, but not basic in the same way as the microscopic motions beneath it. Could space-time be like that? Could distance, duration, and geometry emerge from something deeper, something not spatial in the usual sense and not temporal in the usual sense? Some modern ideas suggest exactly this. They propose that space-time may arise from relationships, from quantum information, from entanglement, from networks of connections, or from structures we do not yet fully understand. In such views, space-time is not the bedrock. It is the smooth surface that appears when an enormous number of deeper ingredients are organised in the right way. That is a strange thought, but not an impossible one. Many familiar things are emergent. A crowd has patterns that no single person possesses. A wave in a stadium moves around the seats, even though each person only stands and sits. The wetness of water is not a property of one isolated molecule in any ordinary sense. Music is not found inside one vibration by itself, but in the arrangement of many vibrations over time. The world we experience is full of properties that appear when smaller parts behave together. So perhaps space-time too is a collective effect. Of course, we should not jump too quickly. It is easy to let imagination sprint ahead of evidence, and physics is at its best when imagination and evidence travel together, like two slightly mismatched hikers who nevertheless agree on the destination. Some theories of quantum gravity suggest tiny building blocks of space. Others suggest that space-time is woven from loops, or strings, or causal relationships, or information shared between quantum systems. These ideas are not all the same, and not all of them can be right. Some may turn out to be stepping stones, some may turn out to be beautiful wrong turns. That is normal. Science often advances not by walking straight to the answer, but by learning which paths do not lead where we hoped. What matters for tonight is not that we settle the question immediately. It is that we begin to understand why the question is so profound. Asking what space-time is made of forces us to examine the assumptions we usually carry without noticing. We assume there is a here and a there. We assume there is a before and an after. We assume that things happen in places and that moments arrive in order. These assumptions work so well in daily life that they feel obvious. But physics has a habit of taking obvious things, turning them gently in the light, and revealing that they are stranger than expected. This is one of the reasons space-time is such a good subject for a quiet evening. It surrounds every moment of our lives, yet it is not something we can hold. It is involved in every movement we make, every breath, every orbit of Earth around the Sun, every beam of light crossing a room. You're not just sitting in space while time passes. You're following a path through space-time. Every object is. A book resting on a table is not motionless in the full sense. It is moving through time, carried along its own world line, aging quietly at its own rate. You're doing the same, though perhaps with better blankets. And if space-time is not fundamental, then that path may be the large-scale appearance of something deeper. The room around you, the distance to the ceiling, the seconds between one breath and the next, may all be part of an emergent structure that becomes smooth only because we are seeing it from far above its smallest workings. Just as a beach looks smooth from a distance but becomes grains of sand when you kneel down, space-time might look continuous because we are enormous compared with whatever lies beneath it. The trouble is that the scale involved is so incredibly small that ordinary images fail us. We cannot simply zoom in with a better camera. We need experiments, theories, and patience. Patience, fortunately, is something this topic rewards. The story of space-time is not a story of one sudden answer. It is a slow unfolding. First, we have to understand how space and time became linked at all. That step alone changed the meaning of reality. It showed that measurements of distance and duration depend on motion, that there is no single universal now shared by everyone, and that the universe is not arranged according to the plain common sense of slow-moving creatures on a small planet. From there, we can follow the idea into gravity, into the vacuum, into quantum fields, into black holes, and finally into the possibility that the world beneath space-time may be built from something more like connection than location. So settle in. Let your shoulders loosen a little. Let the question remain open without needing to be solved too quickly. What is space-time really made of? Perhaps it is geometry. Perhaps it is a field. Perhaps it is woven from quantum information. Perhaps it is not made of anything in the ordinary material sense, but arises from a relationship so deep that space and time are what they look like only from our side of the universe. Whatever the answer turns out to be, the path begins with a simple realization that once seemed almost unthinkable. Space and time, the two quiet measures of our lives, are not separate after all. They belong to one structure, and to understand what that structure might be made of, we first need to see how they became one. To see why space and time became one thing, it helps to begin with the older picture, the one that feels most natural when you're standing in a room and looking around. Space seems to be the place where things are. Time seems to be the order in which things happen. A chair is over there, a lamp is beside it, a book is on the table. Then a minute passes, the lamp is still there, the chair is still there, but perhaps the book has been picked up, opened, and quietly abandoned because the first sentence was too dramatic for bedtime. In ordinary experience, space and time appear to have different jobs. Space gives objects their positions. Time lets those positions change. One tells us where, the other tells us when. They feel so different that for centuries it seemed obvious they must be separate. This older view was not foolish. It worked extremely well. When you walk from one side of a room to the other, you move through space as time passes. The room does not seem to care what time it is. A ruler measures distance, a clock measures duration, and each seems to mind its own business. If two people agree that a table is 2 steps away, they do not usually need to argue about the rate at which Tuesday is occurring. Space seems like a container, and time seems like a river flowing through it. We live as if there is a great invisible grid stretching everywhere, with a universal clock ticking behind the scenes, steady and fair for everyone. It is a comforting picture. It lets trains run on schedules, cakes bake for the right length of time, and people say things like "I will be there in 10 minutes" with at least a faint hope of honesty. Isaac Newton gave this view its most powerful scientific form. In his physics, space and time were absolute. Space existed on its own, whether or not anything occupied it. Time flowed evenly, whether or not anything happened. The universe was like a vast stage with a perfect clock hanging somewhere above it, though hopefully not ticking too loudly. Objects moved across the stage according to laws of motion and gravity. You could describe where something was at one moment, where it would be later, and how it got there. The success of this picture was enormous. It explained falling objects, swinging pendulums, cannonballs, tides, planetary motion, and a great deal of the everyday world. It was not merely useful, it was magnificent. For a long time, there seemed to be no reason to doubt it. Newtonian space and Newtonian time gave physics a clear, stable background. If you and I watched the same event from different places, we might disagree about some practical details. Perhaps I heard the sound later because I was farther away. Perhaps you saw the flash first because you were facing the right direction. But once we corrected for such delays, we assumed there would be a single truth about when the event happened and where it happened. The universe, in that view, had one master record. Space was space, time was time. Everyone was simply reading the same cosmic notebook from different seats. But there was a clue hidden in motion, and that clue had been there all along. Even before Einstein, Galileo had noticed something important about moving observers. Imagine you're inside a smoothly moving ship below deck, with no view of the outside world. If the ship glides at a steady speed over calm water, objects inside behave normally. A dropped ball falls straight down. A cup sits peacefully on a table unless someone bumps it. A sleepy passenger can pour tea with only the usual danger of overfilling it. From inside, you cannot tell by simple mechanical experiments whether the ship is at rest or moving steadily. Motion at a constant speed is relative. It depends on what you compare it to. This insight is gentle but powerful. If you are sitting on a train moving smoothly past a platform, you might say the platform is moving backward while you are still. Someone standing on the platform might say the train is moving forward while they are still. Neither description is absolutely privileged for constant motion. The important thing is the relationship between the observers. Classical physics accepted this for space and motion while keeping time universal. Different observers could disagree about velocity, because velocity depends on comparison, but they were still expected to agree about time. Their clocks, if properly built and synchronized, were supposed to tick at the same rate. This seemed sensible. After all, how could steady motion change time itself? A watch does not know whether it is on a train, in a kitchen, or being worn by someone pretending not to be late. Then light began causing trouble. By the 19th century, scientists had learned that light was connected with electricity and magnetism. It was not just brightness. It was an electromagnetic wave, a travelling disturbance in electric and magnetic fields. This was one of the great achievements of physics, and it came with an astonishing result. The theory predicted a specific speed for light, not a speed depending on the lamp, or the observer, or the weather, but a fixed speed built into the laws themselves. That was strange, because ordinary speeds add and subtract in everyday life. If you throw a ball forward while riding in a carriage, someone standing on the road sees the ball moving with the speed of the carriage plus the speed of the throw. If you walk towards someone in a hallway, The distance between you closes faster than if you stand still. This is so familiar that it barely feels like physics at all. It feels like common sense wearing shoes. Light refused to behave like that. According to the equations of electromagnetism, light in empty space travelled at the same speed in a way that seemed independent of the motion of the source. This raised a difficult question. The same speed relative to what? Waves usually need something to wave in. Sound waves travel through air. Water waves travel through water. So many scientists imagined that light must travel through some invisible medium filling all of space. They called it the ether. The ether was supposed to be perfectly transparent, extremely subtle, and everywhere. It was also, rather inconveniently, impossible to find. If Earth moved through this ether as it orbited the Sun, then light should appear to travel at slightly different speeds depending on whether it moved with Earth through the ether, against it, or sideways. Careful experiments were designed to detect this difference. The most famous of these looked for signs of Earth moving through the supposed ether wind. The expected effect was tiny, but the instruments were clever and precise. If the ether was there, the experiment should have noticed. Instead, the result was stubbornly empty. No ether wind appeared. Light seemed to have the same speed no matter how Earth moved. This was deeply awkward. Physics had two ideas that each seemed well supported. First, the laws of physics should look the same to observers moving steadily relative to one another. Second, light in empty space seemed to have one fixed speed. Keeping both ideas required giving up something else, and the thing that had to go was the old assumption that space and time were separate and absolute. Einstein's great move was to take the speed of light seriously. He did not treat the constant speed of light as a minor technical puzzle to be patched over with hidden machinery. He treated it as a clue about the structure of reality. If all steady moving observers measure the same speed for light, then their measurements of distance and time cannot all remain the same in the old Newtonian way. Something has to adjust. If speed depends on distance and time, and one particular speed is always measured the same, then distance and time themselves must depend on the observer's motion. That is the door through which space and time walk together. This sounds almost unreasonable at first. How can time depend on motion? How can distance change just because one observer is moving relative to another? But the issue is not that objects magically misbehave in some sloppy way. It is that measurement itself is tied to how signals travel, how clocks are synchronized, and how observers compare events. We do not learn about distant things instantly. Light carries information. If light has a fixed speed for everyone, then the meaning of now at a distance becomes more delicate than common sense expects. Consider two lightning strikes hitting the front and back of a moving train. Someone standing on the platform halfway between the strike points might see the flashes arrive at the same time and conclude that the strikes were simultaneous. Someone sitting in the middle of the moving train is moving toward one flash and away from the other. Because light travels at the same speed for both observers, the train passenger receives one flash before the other and concludes that the strikes did not happen at the same time. This is not a trick of bad eyesight. It is not merely that one person failed to correct properly. In Einstein's theory, simultaneity itself depends on the observer's state of motion. There is no single universal now stretching across the entire universe for everyone. That is a quiet earthquake beneath ordinary thought. Once simultaneity becomes relative, time can no longer stand alone as an absolute universal flow. Events that one observer calls simultaneous may be separated in time for another. Likewise, distances measured by observers in relative motion can differ. Moving clocks are measured to tick differently. Moving lengths are measured differently along the direction of motion. These effects are usually far too small to notice in everyday life, because we move very slowly compared with light. A bicycle ride does not make your afternoon noticeably rearrange itself, though it may make your legs complain as if it has. But at high speeds, the differences become real and measurable. Space and time begin to mix. The word mix is useful, though it should not be taken to mean that space becomes time in a simple kitchen recipe sort of way. It means that what one observer separates into distance and duration, another observer may separate differently. The deeper thing is not space alone or time alone, but the combined relationship between events. An event is simply something that happens at a place and a time. A spark flashes, a bell rings, a star explodes, a biscuit is dropped in tea and begins its tragic descent. Each event has both a where and a when. In the older view, everyone could agree on the time order and then separately discuss the spatial distances. In relativity, observers can divide the total structure differently, but the combined space-time relationship remains consistent. This is where Hermann Minkowski entered the story with a new way to understand Einstein's theory. Minkowski had once been one of Einstein's teachers, and he recognized that special relativity was not just a set of odd rules about moving clocks and rulers. It was evidence that space and time form a single four-dimensional structure. He described the world as space-time, where events are arranged not merely in 3 dimensions of space, but also in time. The important point was not simply adding time as another item on a list. People had always known events happen in time. The deeper point was that space and time are linked into one geometry, and different observers slice that geometry in different ways. Imagine a loaf of bread, not because the universe is especially bakery-themed, though that would be comforting, but because a loaf can be sliced at different angles. One person cuts straight slices, another cuts slanted slices. The loaf itself is the same, but each set of slices divides it differently. In a loose way, different observers moving relative to each other divide space-time into space and time differently. One observer's present is like one slice. Another observer's present is tilted differently through the same space-time. The events are part of one larger structure, but the separation into what counts as space right now and what counts as time passing is not universal. This is why space and time became one thing, not because someone simply decided to use a new word, and not because physicists enjoy making reality harder to discuss at dinner. They became one thing because experiments and theory showed that the old separation was incomplete. The constant speed of light forced a new understanding of measurement. The relativity of simultaneity showed there is no universal present. Time dilation and length changes showed that space and time depend on motion in connected ways. Minkowski's spacetime gathered these facts into a single geometric picture. Once that picture was seen, separating space and time completely was like trying to separate the shadow of a tree from the sunlight that makes it visible. You can discuss them separately for convenience, but the deeper relationship is one system. This does not mean our ordinary experience is wrong. It is approximate. In everyday conditions, the differences between observers are so tiny that Newton's old picture works beautifully. That is important. Einstein did not destroy Newton in the simple sense. He showed that Newton's view is a special case, a very accurate approximation when speeds are low and gravity is not extreme. For baking bread, catching buses, building bridges, or wondering whether 5 more minutes in bed will matter, Newtonian time remains perfectly serviceable. It is only when we look closely, move quickly, or require extreme precision that space-time reveals its unity. One of the most practical reminders of this comes from satellite navigation. Satellites orbit Earth with very accurate clocks. Because they move quickly, and because they are higher in Earth's gravitational field than clocks on the ground, their time does not match ours exactly. The differences are small, but small timing errors become large position errors when signals travel at the speed of light. Modern navigation systems have to account for relativity or they drift. That means the unity of space and time is not just an idea for blackboards and late-night conversations. It is quietly helping people find coffee shops, airports, hiking trails, and occasionally the wrong house because the driveway looked similar. Special relativity joined space and time through motion and light. General relativity deepened the union by bringing gravity into the picture. In Einstein's later theory, gravity is not merely a force acting inside space-time. Gravity is connected to the shape of space-time itself. Matter and energy influence that shape, and the shape influences how matter and light move. Once gravity enters, space-time is no longer just a fixed arena where events are arranged. It becomes dynamic. It can curve around stars and planets. It can carry waves. It can expand with the universe. It can become so severely curved near a black hole that even light cannot escape from certain regions. The stage is no longer still. It has become part of the performance. This makes the unity of space and time even harder to avoid. In a gravitational field, time itself runs at different rates depending on position. A clock deeper in gravity ticks more slowly than a clock higher up. This has been measured. It happens near Earth, though gently. It happens much more dramatically near compact massive objects. Space and time are both involved in the gravitational structure. The path of a planet, the bending of starlight, the aging of clocks, and the motion of galaxies all belong to one space-time geometry. The old question, where is it? And the old question, when did it happen, become parts of a larger question about events and relationships. Physics becomes less about objects moving through a silent container and more about patterns in a living geometry. This does not make the universe mystical. It makes it precise in a new way. Space-time is not a mood. It is not a metaphor that can mean anything one likes. It is a measurable structure with clear consequences. Its unity was accepted because it explained real observations and made accurate predictions. The poetry, if there is any, comes after the evidence, not before it. Still, there is something quietly humbling about the shift. We are creatures who experience life one moment at a time. We feel the present as immediate. We remember the past and not the future. We move through rooms, not through four-dimensional diagrams. So space-time is not naturally intuitive. It asks us to trust a view larger than the one our senses provide. That has happened before in science. Earth feels still, yet it spins. The ground feels flat, yet the planet is round. Solid matter feels continuous, yet it is built from atoms and fields with enormous amounts of empty space within. Now, space and time, which feel separate, turn out to be joined. And once joined, they invite a deeper suspicion. If space and time are not separate backgrounds but parts of one structure, then maybe that structure has its own hidden nature. Maybe space-time is not simply the final container of reality. Maybe it is something that can be studied, tested, and eventually understood at a deeper level. Before Einstein, asking what space itself does would have sounded strange. Space did not do anything, it simply was. After Einstein, space-time became active enough that the question of what it is made of could no longer be dismissed as nonsense. If it bends, carries waves, shapes clocks, and responds to matter, then perhaps it has ingredients, or at least a deeper description waiting beneath the smooth geometry. The path from separate space and time to unified space-time was not a matter of replacing common sense with confusion. It was a matter of following consistency. The laws of physics had to agree for observers in steady motion. Light had to keep its measured speed. Clocks and rulers had to be understood not as absolute judges floating outside the universe, but as physical things inside the universe, subject to its rules. Once that was accepted, the old wall between space and time began to fade, not vanish from daily language, because we still need words like here and tomorrow, but fade from the foundations of physics. So when we say space-time, we are not using a fancy synonym for the universe. We are naming the combined arena of events, the structure in which distance and duration are related, the geometry that allows light cones, histories, motion, causality, and gravity to make sense together. Every object traces a path through it. Every clock measures a stretch of it along its own journey. Every beam of light follows its strict, bright route through it. You're not merely occupying a place while time passes over you. You're extended along a path in space-time, from your first moment to this one, and onward into moments not yet reached by your awareness. That may feel strange, but it is also grounding. The same structure that links distant galaxies also includes the quiet room around you. The same laws that make starlight bend near a massive cluster also make satellite clocks need correction, and help explain why time is not a universal river flowing identically for everyone. Space-time is not somewhere else. It is not only in observatories or textbooks. It is what you are in right now, though in daily life it is so smooth and steady that it disappears into the background. And this brings us closer to the next layer of the mystery. Once space and time become one structure, and once gravity becomes the shape and motion of that structure, we have to ask how flexible this structure really is. What does it mean for space-time to curve? How can geometry act like gravity? Why does a planet follow a path as if guided by an invisible slope? And why does light, which has no ordinary weight, still bend when it passes near massive objects? To answer that, we need to leave behind the idea of gravity as a simple pull and step into the quieter, stranger picture of gravity as the stretchy geometry of the universe itself. Gravity is usually introduced to us as a pull. That is the simple version, and for ordinary life it works well enough. Drop a spoon and it falls to the floor, jump into the air and Earth politely invites you back. Toss a ball and it curves downward, unless you're very bad at tossing balls, in which case it may curve sideways into a lamp. We grow up with the sense that gravity is an invisible tug coming from massive things. Earth pulls us downward. The moon pulls the oceans into tides. The sun pulls the planets around itself. It sounds direct, practical, and almost muscular, as if every object in the universe is quietly reaching out and pulling on every other object with invisible arms. For a long time, that picture was more than good enough. Newton described gravity as a force between masses, and his description worked with extraordinary success. It explained falling apples and orbiting moons with the same basic idea. It allowed people to calculate the paths of planets, predict eclipses, understand tides, and eventually send spacecraft across the solar system. A theory does not survive for centuries unless it is doing something deeply right. Newton's gravity did something deeply right. It gave the universe order. It showed that the same laws applied in the heavens and on Earth, which was a remarkable thought at the time. The moon was not wandering through the sky by some separate celestial rule. It was falling around Earth in obedience to the same kind of gravity that makes a raindrop fall from a cloud. But Newton himself knew there was something strange about his picture. Gravity seemed to act across empty space. The sun and Earth were separated by a huge distance, and yet they affected each other. How did Earth know where the sun was? How did the pull travel? Was there some hidden mechanism carrying the influence from one body to another? Newton could calculate gravity beautifully, but he did not claim to know what it really was underneath. In a practical sense, his theory told us how gravity behaves. It did not fully explain what gravity is. Einstein approached the problem from a very different direction. He began by thinking carefully about motion, light, and time, but gravity kept calling him back. There was one clue in particular that mattered. Gravity and acceleration can feel the same. Imagine standing in a small closed room with no windows. If the room is resting on Earth, you feel weight pressing your feet against the floor. Now imagine that the room is far out in empty space, away from planets and stars, but it is being accelerated upward. The floor pushes against your feet in almost the same way. Without looking outside, you might not be able to tell whether you're standing in gravity or being accelerated through space. This simple thought became one of Einstein's guiding ideas. It may sound modest, but it changes the whole story. If gravity can imitate acceleration, perhaps gravity is not an ordinary force after all. Perhaps it has something to do with the structure through which objects move. Einstein spent years working this out, and the result was general relativity, a theory in which gravity is not described as a pull travelling through space, but as the shape of space-time itself. To understand this gently, think about what it means to move naturally. If you are walking across a flat floor, the straight path is simple. If you're walking over a hill, the easiest path may curve. If you're flying across the surface of Earth, the shortest route between two distant cities may look curved on a flat map because Earth itself is curved. Geometry affects motion. The shape of the space you move through influences what counts as a straight or natural path. Einstein extended this idea to spacetime. Objects move along the natural paths available to them, but mass and energy change the geometry of those paths. The Sun changes the spacetime around it, and Earth follows a natural path through that curved spacetime. From our everyday point of view, this looks like a planet being pulled by gravity. From Einstein's point of view, Earth is not being yanked around by a mysterious invisible rope. It is moving as freely as it can through a spacetime that the Sun has curved. This is why people often use the image of a rubber sheet. Place a heavy ball on a stretched sheet and it makes a dip. Roll a smaller ball nearby and it curves around the dip. The image gives a helpful first feeling for curved geometry. Massive objects reshape the arena around them, and other objects follow the changed paths. But the image should be treated gently, not literally. Real space-time is not a rubber sheet sitting inside another space. There is no outside room into which the universe bends in the simple way the sheet bends downward. The bending of space-time is not bending into a larger container we can easily picture. It is a change in the relationships between distances, durations, and possible paths. That is harder to imagine, but it is also more accurate. Gravity is not a dent in something you could touch with your fingers. It is a feature of geometry. Clocks run differently in different gravitational conditions. Light follows curved paths near massive objects. The distances and times measured around a massive body are not arranged as they would be in empty flat spacetime. Geometry has become physical. One of the most striking things about this view is that it explains why all objects fall the same way, at least when air resistance is removed. A feather and a hammer dropped on the moon fall together. In Newton's picture, this is a remarkable balance between gravitational mass and resistance to acceleration. In Einstein's picture, it becomes more natural. The falling objects are not choosing different responses to a pull. They're following the same kind of path through curved space-time. The path depends on the geometry, not on what the objects are made of. A feather, a hammer, a clock, and a sleepy astronaut all obey the shape of space-time. Light also obeys that shape, and this was one of the great early tests of general relativity. Light has no ordinary rest mass, so in a simple pull-based picture, one might wonder why gravity should bend it. But if gravity is curved space-time, then light follows the geometry too. A beam of starlight passing near the Sun should arrive from a slightly shifted direction, because its path through space-time has been bent by the Sun's presence. Observations during a solar eclipse helped confirm this prediction, and suddenly the idea of curved space-time was no longer just an elegant theory. The sky itself had answered. Since then, the evidence has become much stronger. We see light from distant galaxies bent by massive clusters of galaxies, creating arcs and multiple images, as if the universe has built enormous natural lenses. We observe the orbit of Mercury shifting in a way Newton's theory could not fully explain, but Einstein's theory could. We detect gravitational waves, ripples in space-time produced by violent events such as black holes merging far away. These waves travel across the universe, stretching and squeezing distances by incredibly tiny amounts when they pass through Earth. Instruments have measured those tiny changes. Space-time is not merely a mathematical idea resting quietly in books. It can ripple. That word, ripple, is both useful and dangerous. It is useful because it tells us space-time can change and carry disturbances. It is dangerous because it makes us imagine space-time too much like water or cloth. A ripple on a pond is made of moving water. A ripple in fabric is made of moving threads. A gravitational wave is a ripple in geometry itself. It does not need water beneath it or cloth under it. It is a travelling change in the structure of space-time, spreading outward from accelerating masses. When two black holes spiral together and merge, they disturb space-time so strongly that waves carry energy across cosmic distances. By the time those waves reach us, they are faint beyond ordinary imagination, but still detectable with careful instruments. This is where the phrase stretchy geometry becomes helpful. Space-time is geometry, but not stiff geometry. It's not like a frozen grid drawn on glass. It reacts. It can be curved by matter and energy. It can transmit waves. It can be stretched by cosmic expansion. It can become extreme near black holes. Yet it is not stretchy in the way a sweater is stretchy, because a sweater has fibers and exists inside ordinary space. Space-time is the framework that defines ordinary space and time. Its stretchiness means that the measurements of distance and duration are not fixed once and for all. They depend on the distribution of matter and energy. This flexibility affects time as well as space. A clock near a massive object ticks more slowly than a clock farther away. This is not because the clock is damaged or embarrassed by the nearby mass. It is because time itself is measured differently in different gravitational conditions. Near Earth, the effect is small, but it is real. A clock at sea level ticks slightly more slowly than a clock on a mountain. Your feet, being closer to Earth's centre than your head, experience time very slightly differently from your head. The difference is too small to matter for bedtime, though it does mean that technically your hair is a little more ambitious about aging than your socks. Near a black hole, the effect becomes dramatic. To a distant observer, a clock falling toward the edge of a black hole appears to slow more and more. The region near the black hole is not just a place where gravity is strong in the ordinary sense. It is a place where space-time geometry becomes extreme. Paths that once could lead outward no longer do so after a certain boundary is crossed. The future direction for anything inside points deeper inward. This is one reason black holes are so important to the question of what space-time really is. They are places where geometry is pushed close to its limits. But even before reaching black holes, curved space-time teaches us something profound. Gravity is not added to the universe as an extra force acting on top of a fixed background. Gravity is woven into the background, or rather, into the structure that replaces the old idea of a background. The presence of mass and energy changes space-time, and space-time guides the motion of mass and energy. This mutual relationship is very different from the older idea of objects moving through a passive container. The container is involved. The rules of motion and the shape of the arena are part of one conversation. It is tempting to ask whether space-time is therefore a substance. If it can bend and ripple, surely it must be made of something. But general relativity does not answer that question in a simple material way. It describes space-time as geometry, and geometry does not need to be made of little bits in the same way a table is made of atoms. The theory tells us how curvature relates to matter and energy, how objects move, how clocks behave, and how light travels. It does not say that space-time is made of tiny fibers, particles, beads, or cosmic threads. Those ideas may appear in later attempts to combine gravity with quantum physics, but in Einstein's theory itself, space-time is a smooth geometric structure. That smoothness is one of the reasons the theory works so well. At the scale of planets, stars, galaxies, and the universe as a whole, space-time behaves like a continuous geometry. You can imagine paths through it, curves in it, waves across it. There are no obvious cracks. No graininess shows up in ordinary gravitational observations. This smooth description has been tested again and again, and it remains one of the most successful theories ever created. Still, success can hide questions. Water can look smooth from across a lake, even though it is made of molecules. Air feels continuous when a breeze crosses your face, even though it is made of particles. A metal spoon looks solid, though its deeper structure is full of atoms and fields. Smoothness at one scale does not prove smoothness at every scale. General relativity may be the large-scale description of space-time, just as fluid motion is the large-scale description of water. If so, space-time might have a hidden microscopic structure that only appears as smooth geometry when viewed from far enough away. That possibility is one of the great motivations behind the search for quantum gravity. Quantum physics tells us that many things once thought continuous are actually more subtle, or Energy in certain systems comes in discrete amounts. Fields fluctuate. Empty space is not simply nothing. Particles can behave in ways that resist ordinary pictures. General relativity, on the other hand, treats space-time as a smooth, flexible geometry. Bringing these views together is difficult because quantum physics usually assumes a background of space and time in which events occur, while general relativity says that the background itself is dynamical. You cannot simply place quantum rules on space-time as if space-time were a quiet table, because in gravity the table can bend, wobble, and help decide what the rules mean. The stretchy geometry of gravity therefore becomes both a triumph and a doorway. It is a triumph because it explains gravity with astonishing depth and precision. It is a doorway because it makes space-time into something active enough to question. Once geometry can move, curve and ripple, we naturally wonder whether geometry has a deeper origin. Perhaps it is fundamental. Perhaps space-time simply is what it is, smooth and continuous all the way down. Or perhaps smooth space-time is what we get when many deeper quantum ingredients arrange themselves in a certain way, just as smooth air pressure emerges from countless molecules moving around. There's another subtle lesson here. In general relativity, matter and space-time are not independent in the way we might casually imagine. Matter tells space-time how to curve, and curved space-time tells matter how to move. This phrase is often used because it captures the feedback beautifully, but it also hints at a deeper unity. The shape of the universe is not separate from what the universe contains. The stars, galaxies, radiation, and dark matter do not merely sit inside space-time like furniture in a room. They help define the geometry of the room itself. On the larger scales, this relationship becomes cosmology. The universe is expanding, which means the distances between far-apart galaxies grow as space-time itself changes. It is not that galaxies are flying through space from a single central explosion into a surrounding emptiness. Rather, the scale of space between them changes. The geometry of the universe evolves. Gravity, expansion, matter, radiation, and dark energy all enter the story. Space-time is not a fixed box. It has a history. On smaller scales, the same theory explains why clocks and rulers depend on gravity. A person standing near Earth and a satellite orbiting above do not move through space-time in exactly the same way. Their clocks trace different paths through the geometry. This is not just philosophical. Satellite navigation must account for these differences. The devices that help people find their way through city streets rely on the fact that time is shaped by motion and gravity. Every location pin on a phone is, in its quiet way, a small practical tribute to curved space-time, and yet, for all this power, gravity remains gentle in everyday life compared with the other forces of nature. A small magnet can lift a paperclip against the pull of the entire Earth. That fact is surprising when you pause over it. The whole planet pulls downward, but a little magnet wins. Gravity dominates the large-scale universe not because it is strong at the small scale, but because it is always attractive in ordinary conditions and because mass accumulates. Electric charges can cancel each other, positive and negative balancing out, but mass does not cancel in the same way. Stars, planets, and galaxies build enormous gravitational influence because matter adds up. This large-scale dominance makes gravity the architect of cosmic structure. It gathers gas into stars, stars into galaxies, galaxies into clusters. It curves light, slows clocks, shapes orbits, and eventually creates black holes. If space-time is a kind of flexible geometry, then gravity is the way that flexibility shows itself in the presence of matter and energy. The universe is not a collection of objects scattered in an empty warehouse. It is a changing geometry filled with things that help shape that geometry. The beauty of this view is that it transforms falling. A falling object is not simply being dragged downward. It is following the straightest available path through curved space-time. When you sit in a chair, the chair prevents you from following that natural falling path toward Earth's centre. The floor pushes up through the chair, and you feel that push as weight. In a sense, standing still on Earth is less free than falling. A person in orbit drifting inside a spacecraft feels weightless, not because gravity has vanished, but because they and the spacecraft are falling together along the same space-time path around Earth. The result is floating, which looks peaceful, though it probably makes drinking tea inconvenient. Thinking this way takes practice because it reverses ordinary intuition. We think standing on the ground is the natural state, and falling is the disturbance. General relativity says free fall is closer to natural motion, while the ground is what interrupts it. Gravity is not the force you feel while falling. It is the geometry that makes free fall what it is. The force you feel while standing is the floor stopping you from following your natural path. This is a quiet but profound shift. It changes gravity from an invisible hand into the shape of reality around you. The stretchy geometry of gravity also reminds us that our universe is knowable in layers. At one layer, gravity is a pull, and that is enough to understand dropped spoons. At a deeper layer, gravity is curved space-time, and that explains light bending, time dilation, gravitational waves, and the motion of the cosmos. At a still deeper layer, perhaps space-time itself has an origin we do not yet fully understand. Each layer is not simply wrong when a deeper one appears, it becomes part of a larger picture. The pull of gravity is the everyday face of curved geometry. Curved geometry may someday be the large-scale face of something quantum and hidden. So when we ask what space-time is really made of, gravity gives us one of the first serious clues. It shows us that space-time is not nothing. It can have shape, it can have dynamics, it can respond, it can carry waves across billions of years of cosmic history, it can make time run differently from one place to another, and because it can do all this, it becomes difficult to think of empty space as truly empty. The geometry may look calm between the stars, but calm is not the same as absence. Even where there are no planets, no dust clouds, no lamps, no dropped spoons, there may still be fields, fluctuations, curvature, and structure waiting beneath the word empty. That is where the story naturally moves next, away from gravity as the shape of space-time and toward the strange quietness of the vacuum itself. Because once we stop thinking of space as a blank container, the emptiest places in the universe begin to look less like nothing and more like something with secrets. So let us stay for a while in the places where, at first glance, there seems to be nothing at all. Not the dramatic places, not the blazing surface of a star, not the crushed darkness near a black hole, not the busy atmosphere of a planet with weather and birds and someone somewhere wondering where they left their glasses. Let us begin with empty space, the quiet stretches between things, the dark room between the stars, the gap between one atom and the next, the space inside a sealed chamber after nearly every particle has been pumped away. It sounds simple. Empty space should be empty. That is practically its job. It should sit there politely, containing no matter, making no noise, asking for no attention. If there are no particles, no dust, no air, no light, no warmth, and no visible activity, surely we have reached the closest thing the universe offers to nothing. But physics has learned to be suspicious of words like nothing. They are often too clean. Nature rarely respects them for long. The first kind of emptiness we meet is the ordinary kind. A drinking glass may look empty when there is no water in it, but it is full of air. A room may look empty after everyone leaves, but it contains furniture, dust, light, radio waves, heat, and probably a few mysterious crumbs that seem to appear no matter how carefully one cleans. Outer space looks empty compared with Earth, but even between planets there are particles streaming from the sun, magnetic fields, cosmic rays, bits of dust and light crossing from every direction. Even the space between stars is not a perfect void. It contains thin gas, radiation, faint magnetic structure, and the long memory of events that happened far away. So scientists learn to make a more careful kind of emptiness. In laboratories, they build vacuum chambers. They remove air, lower the pressure, reduce contamination, and create environments emptier than anything we normally encounter. These vacuums are useful for studying delicate processes because air molecules are noisy little intruders. They bump into surfaces, carry heat, scatter light, and generally refuse to leave an experiment alone. A good vacuum is like asking a crowd to step out of a room so you can finally hear one quiet instrument. It is not perfect silence, but it is much closer. Even then, empty space does not become nothing. Some particles remain, radiation may pass through, fields remain present, gravity remains. The chamber still exists inside space-time. It still has size and duration. A clock still ticks beside it. A ruler still measures it. Even if you removed every ordinary particle from a region, you would not have removed the physical structure that allows that region to be a region. This is where the question becomes deeper. Empty space is not merely a lack of stuff. It has properties. One of the great changes in modern physics was the realization that fields are not just bookkeeping devices. A field is something spread through space that can have a value at each location and can influence what happens there. The magnetic field around a magnet is a familiar example. You cannot see it directly, but you can see iron filings arrange themselves in patterns, or feel two magnets push and pull. The field is not a solid object, but it is physically meaningful. It stores energy. It carries influence. It can change. It is not nothing. By the time physics developed its modern view of electricity and magnetism, empty space had already become more interesting. Light itself is an electromagnetic wave. That means light can travel through what we call vacuum as a self-sustaining disturbance of electric and magnetic fields. Empty space, then, is not simply a dark container through which light moves like a pebble through a pipe. It is a place where fields can exist and where disturbances in those fields can travel across enormous distances. A beam of starlight crossing the universe is not carried by air, water, or any old-fashioned ether. It is a field disturbance moving through vacuum. The vacuum allows it. Or more carefully, the vacuum is the condition in which that field behaves as freely as possible. That already makes emptiness feel less empty. But quantum physics makes it stranger still. In quantum field theory, which is one of the most successful frameworks in all of science, particles are not usually treated as tiny hard beads moving through an otherwise empty stage. Instead, every kind of particle is connected to a field. The electron has its field. Light is connected with the electromagnetic field. Other particles have their own fields as well. What we call a particle is often described as an excitation of a field, a little packet of activity, a ripple that can be counted and detected. This means that the fields are more basic in the theory than the particles we observe. The particles are what fields do when they are stirred in the right way. Now imagine removing all the particles. You might think that if every excitation is gone, the fields would become perfectly still. But quantum theory does not allow perfect stillness in the ordinary sense. The fields remain, and even in their lowest energy state, they are not like a flat frozen lake. They have quantum uncertainty. They fluctuate. These are not fluctuations like ocean waves you could photograph with a normal camera. They are built into the way quantum fields behave. The vacuum is the state with no real particles present, but it is not a state of absolute blankness. This is often described by saying that empty space seethes with activity. That phrase is vivid, and it can be useful, though it must be handled carefully. It does not mean empty space is full of tiny ordinary particles popping in and out like fireflies in a jar. That image can become misleading if taken too literally. The vacuum fluctuations of quantum fields are not little marbles borrowing existence in a cartoonish way. They are features of the quantum fields themselves, subtle patterns of uncertainty and possibility that affect measurable things. The vacuum may not be crowded in the everyday sense, but it is not dead. One of the famous signs of this hidden activity is the Casimir effect. Imagine two very smooth metal plates placed extremely close together in a vacuum. Quantum fields are present both outside and between the plates, but the plates restrict which field fluctuations can fit between them. The result is a tiny force pushing the plates together. It is not caused by ordinary air pressure, since the setup is in vacuum. It comes from the structure of the quantum vacuum itself. That is a remarkable thought. Empty space can produce a measurable effect because the fields within it have allowed and disallowed patterns. The vacuum has behavior. Another sign comes from the way atoms interact with the vacuum. In certain situations, excited atoms lose energy and emit light. We may describe this as an atom deciding to drop to a lower energy state, but the quantum vacuum plays a role in allowing that process. The surrounding field is not merely absent, it participates in the probabilities of emission. Even the properties of particles can be influenced by their interaction with quantum fields in the vacuum. What we measure as the mass or charge of a particle is not always just a bare isolated property. It is shaped by the particle's relationship with the fields around it. This means that empty space is not a passive void waiting for particles to enter. It is more like the ground state of a vast system of fields. Ground state sounds calm, and it is calm in the sense that it is the lowest energy arrangement available, but lowest does not mean featureless. A sleeping cat is still a cat, even if it is not currently knocking something off a shelf. The vacuum is the quietest state of quantum fields, but it still has structure. This idea changes how we think about the word empty. In everyday language, empty means nothing useful is there. An empty cup contains no tea. An empty wallet contains no cheerful surprises. But in physics, empty space may be empty of particles while still filled with fields, laws, geometry, fluctuations, and possible excitations. It is not a material substance in the old sense, yet it is not a blank nothing. It is a physical state. Gravity adds another layer. In general relativity, even a region with no matter can have spacetime geometry. The geometry may be flat, curved, expanding, or carrying gravitational waves. A region of space can be empty of particles, but still not be simple. A gravitational wave can pass through a vacuum. Light can cross it. The expansion of the universe can affect it. Curvature can exist because of distant matter or boundary conditions. So even before quantum physics enters, empty space in Einstein's universe is not necessarily a lifeless backdrop. It is part of the gravitational structure. Then cosmology makes the vacuum even more important. The universe is expanding, and observation suggests that this expansion is accelerating. One way physicists describe the cause of this acceleration is through something called dark energy. The simplest version behaves as though empty space itself has an energy associated with it, an energy that does not thin out as space expands in the ordinary way matter does. This is an unsettling idea. We usually think that if you make a box larger while keeping the same amount of stuff inside, the contents become more spread out. But dark energy, in its simplest description, is tied to space itself. More space means more of this vacuum-like energy. That energy affects the expansion of the universe. No one should pretend this is fully understood. Dark energy is one of the major open problems in physics. It may be vacuum energy. It may be something more subtle. The calculations connecting quantum vacuum energy to cosmic expansion lead to one of the most famously difficult mismatches in theoretical physics. The predicted amount and the observed amount do not agree in any simple way. This is not a small bookkeeping mistake like losing a receipt in a coat pocket. It is a deep problem, a sign that our understanding of quantum fields, gravity, and space-time is incomplete. Empty space, once again, refuses to be simple. That incompleteness is important for our larger question. If space-time were just an empty stage, then vacuum would be dull. It would be the place where nothing happens. But instead, vacuum is where some of the deepest tensions in physics appear. Quantum fields tell us the vacuum has fluctuations and structure. Gravity tells us space-time geometry can exist without matter. Cosmology suggests the vacuum may influence the fate of the universe. Black hole physics suggests that the vacuum near horizons is not the same for all observers, and that what counts as a particle can depend on motion and gravity. The more carefully we inspect emptiness, the more it becomes a meeting point for the biggest theories we have. Let us slow down with that thought. What counts as empty may depend on the observer. In quantum field theory in curved spacetime, the idea of a particle can become observer-dependent. An observer moving in one way may describe a field as being in vacuum, while another accelerated observer may detect something like warmth. This is not a detail most people need while making breakfast, but it matters for fundamental physics. It suggests that particles are not always the most basic or universal way to describe reality. Fields and space-time structure may be deeper. What one observer calls no particles may not be described in exactly the same way by another observer moving differently. This is very different from the older idea of empty space as a universal nothing. A universal nothing should look like nothing to everyone, but the quantum vacuum is tied to the state of fields, the motion of observers, and the geometry of space-time. It is not a simple absence, it is a relational physical condition. The word relational is useful here. Many things in physics are not absolute in isolation but depend on relationships. Motion depends on what you compare it to. Time intervals depend on paths through space-time. Energy can depend on reference frame. Now, even emptiness begins to show a relational character. To ask whether a region is empty, we must ask empty of what, according to whom, under what conditions, and at what scale. That may sound like physics making a simple question unnecessarily fussy, but the universe has earned the fuss. At human scales, we can still use ordinary emptiness. A room without people is empty enough for conversation. A vacuum chamber with few particles is empty enough for experiments. Interstellar space is empty enough that a spacecraft can coast for years without hitting much. But at the foundational level, emptiness becomes rich. It includes fields in their lowest states, quantum fluctuations, space-time geometry, possible curvature, and perhaps vacuum energy. The nothing of physics is not nothing in the philosophical sense. It is the least excited state of something. That phrase, the least excited state of something, is a quiet revolution. It means that the vacuum is not the opposite of reality. It is one of reality's conditions. It is what remains when ordinary particles are removed, but the underlying fields and space-time remain. If particles are ripples in fields, then empty space is not the absence of the ocean. It is the ocean when there are no large visible waves. Even calm water has depth, pressure, temperature, and microscopic motion. The analogy is not perfect, but it gives the right mood of caution. Calm does not mean non-existent. There is another way to feel this. Think of a musical instrument in a silent room. If no one plays it, no note is heard. But the instrument is not nothing. It has strings, shape, tension, and possible sounds. Touch it lightly, and it responds in certain ways rather than others. The quantum vacuum is a bit like that, though not literally made of strings in the everyday sense. The fields are present. Their possible excitations are determined by their nature. Particles are like notes that can be played. Empty space is not the absence of the instrument. It is the instrument at rest. This view also helps explain why the properties of empty space matter for the particles that appear within it. A particle is not a lonely object inserted into blank nothing. It is an excitation of a field that already belongs to the vacuum structure. Its behavior depends on the field, and the field's behavior depends on the rules of the vacuum. If different fields fill the universe, then what we call space is not merely a container, but a setting of physical possibilities. The vacuum tells particles how they may exist, move, interact, appear, vanish, and transform. There is a famous example involving the Higgs field. Unlike many fields whose lowest state can be thought of as having no average value, the Higgs field has a non-zero background presence throughout space. Particles interact with this field, and that interaction is part of why many particles have mass. The details are subtle, and we do not need to chase them too far tonight. What matters is the broader lesson. Empty space is not empty even in the sense of having no field activity. Some fields have a constant presence that affects the basic properties of matter. The vacuum is not a featureless void through which particles merely pass. It helps define what particles are. This is one reason the old phrase empty space can feel almost charmingly misleading. It is like calling a library empty because no one is currently speaking. The shelves are still there, the books are still there, the meaning is still there, waiting. Empty space contains the fields whose excitations become matter and radiation. It contains the geometry through which those excitations move. It may contain vacuum energy that shapes cosmic expansion. It contains the rules of what can happen. Yet we should remain grounded. Empty space is not secretly packed with usable energy in the simple, fantasy sense. It is not a cosmic battery waiting for someone to plug in a kettle. Vacuum energy and quantum fluctuations are real concepts, but they do not mean one can casually extract unlimited power from nothing. Physics is generous with wonder but strict with accounting. The vacuum has structure, but that structure obeys laws. It is not magic disguised in a lab coat. This balance matters because the vacuum is often described in exaggerated ways. People hear that particles pop in and out of existence, or that empty space has infinite energy, or that the vacuum is a bubbling foam and the imagination quickly runs ahead. Some of those phrases point toward real mathematical ideas, but taken literally they can become confusing. The better picture is quieter. Empty space is the lowest energy state of quantum fields, shaped by uncertainty, capable of measurable effects, embedded in space-time geometry, and perhaps connected with the expansion of the universe. That is already strange enough. We do not need to decorate it with fireworks. The deeper lesson is that absence itself has physics. Remove the air, remove the dust, remove the light, remove the ordinary particles, and you still have not removed the quantum fields. You still have not removed space-time. You still have not removed the possibility of measurement, motion, and change. The vacuum is what remains when the universe is made as quiet as possible, and quiet is not the same as blank. This brings us back to the question of what space-time is made of. If empty space contains fields, then perhaps one might think space-time is just the collection of those fields. But that is not quite right. At least not in our current theories. Quantum fields are usually described as existing on space-time, while general relativity describes space-time itself as something dynamic. The fields are not simply the same thing as space-time. They live in it, respond to it, and in turn contribute energy and momentum that can influence its curvature. The relationship is intimate but not fully unified in our present understanding. Here lies the tension. Empty space in quantum theory is full of field structure. Empty space in relativity is geometry, possibly curved and dynamic. Empty space in cosmology may carry dark energy. We have several powerful ways to speak about the vacuum, and each captures something real, but fitting them into one complete picture remains difficult. That difficulty may be a clue that space-time and fields are not independent ingredients at the deepest level. Perhaps both emerge from a more fundamental framework, or perhaps space-time is fundamental, and fields are its contents, or perhaps fields are fundamental, and space-time is a pattern in their relationships. These are not bedtime questions in the sense of being easy, but they are excellent bedtime questions in the sense that they are large enough for the mind to drift inside them without bumping into the walls too quickly. When we look into the night sky, the darkness between stars seems empty, but that darkness is crossed by ancient light, shaped by gravity, filled with fields, stretched by expansion, and alive with quantum possibilities too faint for ordinary senses. The quiet is real, but it is not the quiet of non-existence. It is the quiet of something deeply ordered, something waiting in its lowest voice. Even the space inside you and around you participates in this. The atoms in your body are mostly not solid in the everyday picture of packed material. They are structured by fields and forces, with space between nuclei and electrons that is not a simple void. The room around you is full of electromagnetic fields, thermal radiation, gravitational influence, and the persistent ground state of quantum fields. You're not resting inside nothing. You're resting inside a layered physical reality whose calm surface hides astonishing depth. So empty space is not a blank stage. It is closer to a quiet ocean of fields and geometry, though even that image must be used gently. It is the condition from which particles can arise, through which light can travel, in which gravity can curve paths, and across which the universe itself expands. It is not empty in the ordinary sense. It is simply as empty as the laws of physics allow, and once we accept that, the next thought begins almost by itself. If empty space is filled with fields, and particles are excitations of those fields, then perhaps the material world is not made of little solid things at the deepest level. Perhaps what we call matter is more like music played by invisible fields that fill the universe. To understand space-time more deeply, we have to listen to those fields, to the particles they create, and to the quiet ocean beneath reality that makes the visible world possible. The moment empty space stops being nothing, the whole picture of reality begins to change. It becomes harder to imagine the universe as a collection of little solid objects moving through a blank container. That picture is comfortable, and it is not completely useless. It works well enough when we are thinking about stones, chairs, planets, spoons, and the familiar things that seem to have firm edges and definite locations. A stone appears to be a lump of matter. A chair appears to be a shaped object. A planet appears to be a sphere moving through space. But when physics looks more closely, solidity starts to soften. The world that seemed to be made of things begins to look as though it is made of activity. This is where fields enter the story. A field is one of those ideas that sounds simple at first, then quietly becomes enormous. In ordinary language, a field might mean a meadow, perhaps with long grass, a fence, and one sheep looking slightly suspicious of the weather. In physics, a field means something spread out through space and time, something that has a physical value at each place and can influence what happens there. You already know fields through experience, even if you do not usually call them that. Hold a magnet near a refrigerator door and you feel an invisible influence. Bring a compass near a wire carrying electric current, and its needle turns. Stand in sunlight, and electromagnetic fields are delivering warmth and vision across empty space. The field is not seen directly in the way a chair is seen, but it acts, and because it acts, physics treats it as real. The older mechanical imagination wanted the world to be built from pieces. Tiny particles, tiny gears, tiny balls, tiny hard bits bumping into each other. That picture made sense in a world where matter seemed solid and contact seemed essential. One object pushed another because they touched. One billiard ball struck another and sent it rolling. If something happened at a distance, such as a magnet pulling a nail, that felt mysterious. A field gives a different kind of explanation. The magnet changes the magnetic field around it. The nail responds to that field. The influence is not a hand reaching invisibly across emptiness. It is a condition present in the space between them. This way of thinking became especially powerful with electricity and magnetism. Electric charges create electric fields. Moving charges create magnetic fields. Changing electric and magnetic fields can sustain one another and travel outward as light. Suddenly, light itself was no longer just a stream of brightness, or a mysterious substance emitted by glowing things. It was a wave in fields, an electromagnetic disturbance crossing space. The same basic framework could explain magnets, sparks, radio waves, heat radiation, visible light, and much more. It was as if nature had been speaking in one language through many different accents. But quantum physics changed the meaning of fields again. In modern physics, fields are not merely smooth, invisible influences surrounding particles. They're often treated as more fundamental than particles themselves. Every kind of elementary particle is associated with a field that fills the universe. There is an electron field, and what we call an electron is a particular excitation of that field. There are quark fields, and quarks are excitations of those fields. There is the electromagnetic field, and photons are excitations of it. Other forces and particles have their own fields as well. The visible world becomes a pattern of field activity. This is a strange shift. We are used to thinking of a particle as a tiny object, something like a microscopic grain. It may be very small, but we still imagine it as a little thing with a little location, travelling along a little path. Quantum field theory asks us to think differently. A particle is not a tiny bead sitting on top of a field. It is more like a localized disturbance in the field, a packet of energy and behavior that can be created, detected, absorbed, or transformed. The field is everywhere. The particle is what the field is doing in a certain way. A useful image, though not a perfect one, is a quiet lake. A wave rises on the surface, travels for a while, and disappears into other waves. The wave is real. It can carry energy. It can rock a boat. It can be measured. But it is not a separate little object made of a wave substance. It is a pattern in the water. In quantum field theory, particles are somewhat like patterns in fields. The analogy must be kept gentle, because quantum fields are not literal water, and particles are not ordinary waves. But the image helps loosen the old idea that matter is made from hard specks moving through emptiness. This means that the universe is not filled with fields only where particles happen to be. The fields are present everywhere, even where no particles are detected. Empty space is not empty because the fields remain in their lowest energy states. When enough energy is added in the right way, a field can produce particles. When particles interact, fields are exchanging energy, momentum, and information according to strict rules. What appears to us as matter is the stable, organized activity of fields. The electron is a good example because it is familiar enough to appear in school books, and strange enough to remind us that schoolbooks are only the beginning. Electrons are found around atoms. They help make chemistry possible. They allow electricity to flow through wires. They help determine the structure of matter, the colour of materials, the bonds in molecules, and the behaviour of the devices that surround us. But in the deeper modern view, an electron is not a tiny planet orbiting a tiny sun, even though that image has been used far too often because it is easy to draw. An electron is an excitation of the electron field. Every electron in the universe is an excitation of the same underlying kind of field. This is why electrons are identical. One electron is not handcrafted with its own little personality. They are instances of the same field behaving in the same particle-like way. That identity is remarkable. Two pebbles can look similar but are never perfectly identical. They have different shapes, scratches, histories, and degrees of commitment to being underfoot at the worst possible moment. Electrons, however, are indistinguishable in a much deeper sense. Every electron has the same charge, the same mass, the same basic quantum properties. This makes sense if electrons are not individual manufactured objects, but excitations of one universal field. The field gives them their shared nature. The same kind of thinking applies across the known particles. Quarks make up protons and neutrons. Gluons are associated with the strong force that binds quarks together. Photons carry electromagnetic interactions. Other particles appear in high-energy processes and in the early universe. The standard model of particle physics organizes these fields and their excitations with astonishing success. It is not a complete theory of everything, especially because gravity does not fit into it in the same way, but within its domain, it is one of the most precise descriptions of nature ever built. Forces also look different in this picture. In older language, one might say that particles exert forces on each other. In field language, particles interact through fields. Electromagnetism is mediated by the electromagnetic field. The strong and weak nuclear forces have their own fields and particles associated with them. Interactions are not little invisible ropes connecting isolated objects. They are changes and exchanges within an underlying field framework. Reality becomes less like a clockwork machine filled with solid cogs, and more like a set of overlapping, interacting activities spread throughout space. The word overlapping matters. The fields of modern physics do not take turns filling the universe. They all exist together. The electromagnetic field is present. The electron field is present. Quark fields are present. The Higgs field is present. Other fields are present. At every point, the vacuum is not just one quiet thing, but a layered condition, involving many fields in their lower states. When something happens, it is often because several fields are interacting. A particle can decay into other particles, light can be emitted or absorbed, matter can scatter, energy can move from one field into another according to the rules of the theory. The Higgs field gives a particularly important lesson about the vacuum. Unlike many fields, the Higgs field has a background value throughout space. It is not something that turns on only inside matter. It is part of the vacuum structure. Many elementary particles interact with it, and that interaction is connected with their masses. This does not mean the Higgs field is a thick syrup slowing particles down, a metaphor sometimes used but not quite right. It means that the properties of particles are shaped by their relationship with the field that is present everywhere. What we call empty space helps determine what matter is like. That is a profound idea. The mass of a particle, one of the things that makes matter feel substantial, is not simply an isolated possession of a tiny object. It is tied to fields that fill the vacuum. The vacuum is not an empty room where particles bring their properties in their pockets. It is part of the system that gives those properties meaning. This field-based view also helps explain why high-energy experiments can create particles. In particle accelerators, particles are smashed together at enormous energies, not because physicists dislike particles, but because concentrated energy can excite fields in new ways. New particles can appear as field excitations if the conditions allow. They may exist briefly, decay quickly, and leave traces in detectors. The detectors do not usually see the tiny particle itself in the simple visual sense. They record tracks, energy deposits, flashes, and patterns. From those patterns, physicists reconstruct what field excitations must have occurred. This is one reason particle physics can seem so removed from everyday intuition. At the deepest level we can reach experimentally, matter is not a set of miniature objects photographed directly like pebbles on a table. It is inferred through interactions. It is known through patterns in fields, probabilities, energies, and detector responses. That does not make it unreal. It makes it subtler than our senses evolved to handle. Our eyes and hands are wonderful instruments for fruit, faces, weather, and avoiding furniture in the dark. They were not designed to intuit quantum fields. Still, the effects of fields are everywhere in daily life. The reason your hand does not pass through a table is not that the matter in your hand and the matter in the table are solid in a simple packed sense. Atoms are mostly structured space with tiny nuclei and surrounding electron behavior. What you feel as solidity comes largely from electromagnetic interactions and quantum rules governing electrons. The particles in your hand and the particles in the table resist being pushed into the same states and configurations. The sensation of touch is field interaction, interpreted by nerves and brain. Solidity is real as an experience, but its cause is not little hard pieces touching in the old-fashioned way. It is fields and quantum structure. A wall looks continuous, but at the atomic scale it is mostly not filled in the way a brick wall appears filled at human scale. The reason it stops you is not because there is literally no empty gap anywhere. It is because the fields and particles that make up you and the wall interact in ways that produce resistance. The ordinary world is stable because quantum fields have organized themselves into atoms, molecules, materials, and living bodies. The quiet ocean beneath reality is not chaotic noise, it has rules that allow structure. That phrase, quiet ocean, is an image, and like all images in this subject, it should not be mistaken for a literal substance. The fields are not floating in a cosmic sea. They are the ingredients of the theory, spread through space-time, capable of excitations. But ocean is helpful because it reminds us that what we call particles are not necessarily separate from the underlying medium of description. A wave is not other than water. A particle is not other than its field. The visible world is the field world becoming active in stable, countable ways. Yet this raises a deeper question for our main subject. If fields fill space-time, are fields what space-time is made of? The answer is not straightforward. In our usual quantum field theories, fields are defined on space-time. They need space-time as the arena in which they have values, change, interact and propagate. Space-time tells us what counts as nearby, what counts as before and after, how signals travel and how energy and momentum are described. The fields live in space-time, so simply saying space-time is made of fields would be too quick. At the same time, fields influence space-time. In general relativity, energy and momentum affect curvature. Fields carry energy. Matter is field excitation. Radiation is field excitation. The vacuum may have energy. All of that can contribute to the gravitational behavior of space-time. So space-time and fields are not strangers. They are deeply linked. Fields need space-time in ordinary theory, and space-time responds to the energy of fields. This relationship is intimate but incomplete. It is like hearing two instruments playing together beautifully while suspecting that somewhere underneath there is a deeper score neither instrument fully explains by itself. This is the unresolved meeting place between quantum field theory and gravity. Quantum field theory works best when space-time is treated as a fixed background, or at least as a given stage. General relativity says the stage is not fixed. It is dynamic. It curves, expands, ripples, and participates. If fields require space-time, and space-time responds to fields, then a complete theory should describe both together without giving one an unfair advantage. That is difficult. It is one of the reasons physicists search for quantum gravity. There are situations where this difficulty cannot be ignored. Near the center of a black hole, general relativity predicts extreme curvature, where the theory appears to break down. In the very early universe, energy densities were so high that quantum effects and gravity both mattered. Near black hole horizons, quantum fields in curved space-time lead to surprising effects, including the idea that black holes are not perfectly black, but can emit radiation through a subtle quantum process. These are not places where one can comfortably use quantum fields on a simple fixed stage and forget about geometry. Nor can one use smooth geometry and ignore quantum behavior. The deep structure of reality presses through the cracks. The vacuum itself becomes one of those cracks. Quantum fields say the vacuum has fluctuations and structure. Gravity says energy affects space-time. But if vacuum energy gravitates, then why does the universe not curve or expand in a way wildly different from what we observe? This is part of the dark energy puzzle and the cosmological constant problem. It is a sign that our understanding of the vacuum is incomplete when gravity is included. The quiet ocean may be quieter, stranger, or more delicately balanced than our current theories can explain. This is why the question of what space-time is made of cannot be separated from fields and particles. The matter we see is not built from hard little things in empty nothing. It is built from field excitations in a vacuum full of structure. The forces that bind matter are field interactions. The properties of particles depend on the vacuum and the fields present throughout it, and space-time, while not simply identical to these fields in our current theories, is affected by them and provides the setting in which they make sense. A helpful way to hold this without forcing an answer too early is to think of reality as layered. At the human layer, the world contains objects. Cups, stars, bodies, doors, beds, curtains, lamps, books. At a smaller layer, those objects are made of atoms and molecules. At a still deeper layer, atoms are built from quantum particles. Deeper still, particles are excitations of fields. Beneath the ordinary idea of emptiness, the vacuum is the low-energy state of those fields. Surrounding and structuring all of this is spacetime, whose geometry can bend and evolve. The open question is whether spacetime belongs at the bottom of the stack, or whether it too is an emergent pattern from something deeper. Some modern ideas suggest that fields and spacetime may arise together from more basic quantum information. Others suggest that spacetime may be built from networks of relationships, and fields appear as patterns within them. Still others keep spacetime closer to fundamental, and try to quantize gravity as another field, with hypothetical particles associated with gravitational interaction. These ideas differ greatly, and none has yet become the final accepted answer. But they all take seriously the lesson that the old separation between objects and emptiness is gone. The vacuum has structure, fields are everywhere. Particles are excitations, spacetime is dynamic. Something deeper is being hinted at from several directions at once. For a sleepy mind, this can be oddly calming. The world is not less real because it is made of fields rather than tiny solid pellets. It is more deeply real than the simple picture allowed. A wooden table is still a wooden table. It still holds a cup, supports a book, and bruises a shin if encountered too confidently at night. But beneath its familiar surface is a vast arrangement of quantum fields, electromagnetic interactions, atomic structures, and space-time geometry. Reality has not vanished into abstraction. It has become layered. The same is true of you. Your body is made of atoms, yes, but those atoms are organized field activity. The warmth of your skin, the signals in your nerves, the chemistry of your cells, the light entering your eyes, the sound of this narration reaching your ears, all of it depends on fields interacting. You're not a separate solid object placed inside a dead void. You're a stable, living pattern in the same field-filled universe that produces stars, dust, light, and galaxies. That does not make you less individual. It simply means your individuality is built from processes that run deeper than everyday language can easily capture. And perhaps space-time itself is like that too. Perhaps it feels smooth and continuous because we encounter it at a large scale, just as the table feels smooth beneath your hand even though its deeper structure is complex. Perhaps the fields we know are not the final ocean, but waves on something still deeper. Perhaps space-time is the calm surface of a quantum sea whose smallest motions are hidden from us by the enormous gap between human scale and the scale where gravity and quantum uncertainty meet. This is where we begin to approach one of the strangest possibilities in physics. If fields are never perfectly still, and if space-time itself must somehow be brought into the quantum world, then the smooth geometry of Einstein may become restless at the smallest distances. Empty space may not remain smooth when viewed closely enough. The quiet ocean may develop foam, not ordinary foam made of bubbles of course, but a restless uncertainty in geometry itself, where the familiar ideas of distance and duration begin to lose their clean edges. That is the next step into the smallest scales, where physicists wonder whether space-time has a grain, a limit, or a hidden texture too fine for any ordinary instrument to see. If we follow the idea of fields all the way down, past atoms, past nuclei, past the particles that once seemed like the final furniture of the universe, we eventually arrive at a scale where our usual pictures begin to fail, not just become difficult. Fail in the way a paper map fails when you try to use it to navigate the surface of a soap bubble. The rules that work so well at familiar sizes start asking for corrections. The smooth space-time of Einstein, so elegant across planets and stars, meets the restless uncertainty of quantum physics. And in that meeting place, physicists have imagined one of the strangest possibilities in all of science, that space-time itself may not remain smooth when viewed at the smallest possible distances. This is where the idea of quantum foam enters. It is a phrase that sounds almost playful, as if the universe has been quietly preparing a cosmic cappuccino, but the idea behind it is serious. Quantum foam refers to the possibility that, at incredibly tiny scales, space-time may become turbulent, fluctuating, and uncertain. The clean geometry we use to describe space and time might break down into something much more restless. Distances might no longer be sharply defined. The order of events might become less clear. Tiny distortions of geometry might flicker in and out of relevance. The familiar surface of reality may be smooth, only because we're far too large to notice what happens underneath. The phrase is associated with the physicist John Wheeler, who liked bold ideas and memorable language. Wheeler imagined that if we could examine space-time at extremely small scales, it might not look like the smooth fabric described by general relativity. Instead, it might look frothy, irregular, and active, with tiny fluctuations in geometry appearing everywhere. Not foam made of bubbles in space, because that would still assume space is already there in the ordinary way. Rather, foam as a metaphor for space-time itself becoming restless. The arena of physics would no longer be a calm stage. It would be shaking at the level where gravity and quantum uncertainty meet. To understand why anyone would think such a thing, we need to bring two great ideas together. The first comes from quantum physics. At small scales, nature does not behave like a tiny version of the everyday world. Particles do not always have perfectly definite positions and speeds at the same time. Fields do not sit in perfect stillness even in vacuum. Energy and time, position and motion, measurement and uncertainty all have relationships that prevent nature from being pinned down with unlimited sharpness. Quantum physics is not just a theory of small objects, it is a theory of limits on certainty. The second idea comes from general relativity. Gravity is geometry. Matter and energy affect space-time curvature. The shape of space-time affects the motion of matter and light. This means that energy is not merely something inside space-time. It also helps determine the geometry of space-time. If quantum physics says that energy in fields cannot be perfectly still or sharply fixed, then perhaps space-time itself cannot remain perfectly fixed either. The geometry should feel the quantum restlessness of the fields within it, and if gravity itself is to be quantum, then the geometry may have its own uncertainty as well. That is the heart of the quantum foam idea. At large scales, the tiny fluctuations average out, and space-time appears smooth. At the smallest scales, those fluctuations might dominate. The smooth road becomes gravel. The calm sea becomes froth. The clean lines of geometry become blurred. Not because our instruments are bad, though they certainly are nowhere near powerful enough to see this directly, but because the concept of a perfectly smooth distance may no longer apply. There is a scale where physicists expect this trouble to become unavoidable. It is called the Planck scale, named after Max Planck, one of the founders of quantum theory. The Planck length is unimaginably small. It is far smaller than an atom, far smaller than a proton, far smaller than anything current experiments can directly resolve. If an atom were enlarged to the size of Earth, the Planck length would still be far below ordinary human intuition. Comparisons quickly become silly, rather like trying to explain the size of a grain of sand by comparing it to a galaxy, and then realizing you've not made anyone feel calmer. The Planck scale is not known to be a literal smallest length, in the simple sense of a final pixel of space. That is important. It is not as though physicists have definitely discovered tiny square tiles from which space is built. The Planck length is more like a warning sign created by combining the constants of quantum physics, gravity, and the speed of light. It tells us that around this scale, our current theories are expected to stop working together in the usual way. It is the scale where quantum effects of gravity should become strong. It is where space-time may no longer be safely treated as smooth. If you try to measure an extremely tiny distance, you need to use something with a very short wavelength, which means very high energy. That is already a quantum problem, but if you concentrate too much energy into too small a region, gravity becomes important. In the extreme case, the region could collapse into a tiny black hole. So there is a strange tension. To see smaller, You need more energy, but too much energy packed into too little space changes the space-time you are trying to inspect. The act of probing the smallest distances may disturb the very geometry being measured. Nature seems to say, quite politely but firmly, that below a certain scale our usual idea of measurement may not make sense. This is different from merely having poor technology. We might someday build better microscopes, stronger accelerators, more precise detectors, and still face a conceptual limit. A normal microscope fails to see atoms because visible light is too coarse, but other methods can reach atomic scales. At the Planck scale, the problem may be deeper. The attempt to define a smaller and smaller location may require such energy that location itself becomes unstable. The measuring tool becomes part of the gravitational problem. The ruler bends the space it measures. Eventually, the idea of a ruler may stop being appropriate. This is why the question of smallest possible distances is so delicate. Does space have a smallest unit? Is there a shortest meaningful distance? Or is space continuous but impossible to measure below a certain scale because of quantum gravity? Different theories answer differently. Some suggest that areas or volumes may come in discrete amounts, not as ordinary cubes or blocks, but as quantum units of geometry. Others suggest that the idea of distance emerges from deeper relationships and has no meaning below a certain level. Some theories keep space-time smooth in one sense, but change how particles and fields behave at extreme energies. No single answer has been confirmed. Loop quantum gravity, for example, is one approach in which geometry itself becomes quantized. In this view, space is not made of tiny beads in the ordinary sense, but geometric quantities such as area and volume have discrete spectra. The deep structure is sometimes described through networks of relationships, with space-time geometry emerging from them. The picture is not a simple grid. It is more subtle, more relational, and much harder to visualize. If something like this is right, then space-time may have a granular structure, though not a grain like sand or salt. More like a quantum pattern that only looks smooth at larger scales. String theory takes a different route. It suggests that what we call particles may arise from tiny vibrating strings, and gravity appears naturally through one of their possible vibration patterns. In many versions, the theory requires extra dimensions and brings space-time into a larger mathematical structure. It also introduces the idea that extremely short distances may not be accessible in the usual way, because strings have extended size rather than being perfect points. Again, this does not give us a simple picture of space made of tiny blocks. It suggests that the deepest ingredients of reality may not fit the categories we use in everyday life. Other ideas look to causal sets, where space-time is built from discrete events and the causal relationships between them. In such a picture, what matters most is not a smooth background, but the ordering of events. What can influence what? Space-time as we know it would emerge from a huge number of these basic causal relationships. This is appealing because causality is central to relativity. Light cones, cause and effect, and the order of possible influence are all built into space-time. Maybe those relationships are more fundamental than distances themselves. Still, other approaches focus on quantum information and entanglement. In these views, the connectedness of quantum systems may be tied to the emergence of spatial geometry. Distance might not be basic. It might be a way of describing how strongly or weakly parts of a deeper quantum system are related. This sounds strange, but it has gained attention because of surprising links between gravity, black holes, thermodynamics, and information. The more physicists study space-time, the more often information appears at the edge of the discussion, like a quiet guest who may have been important all along. Quantum foam is not itself a complete theory. It is more like an image for what many theories expect, that space-time at the smaller scales cannot be a perfectly smooth classical geometry. But the details remain uncertain. Does space-time flicker violently? Does it become discrete? Does it dissolve into relationships? Does it remain smooth, but with quantum states rather than definite shapes? These questions are still open, They're not open because physicists have not thought hard enough. They're open because the scale is so far beyond direct experiment that nature has made the answer very difficult to reach. This is one of the practical challenges of quantum gravity. To test physics at the Planck scale, directly, would require energies far beyond anything we can produce. Our most powerful particle accelerators are enormous achievements, but they are still nowhere near the energies needed to probe Planck scale structure head-on. So physicists look for indirect clues. They study black holes. They study the early universe. They look for tiny violations or modifications of known symmetries. They examine cosmic rays, gravitational waves, and the faint afterglow of the early cosmos. They ask whether light from very distant explosions might show tiny delays depending on energy, which could hint at space-time structure. So far, no clear confirmed sign has settled the matter. The absence of direct evidence does not make the question empty. It means the question is hard. Many of the greatest advances in physics began with tensions between theories long before direct tests were possible. But it also means we should be careful. Quantum foam is a plausible and influential idea, not a photographed landscape. No one has taken a snapshot of space-time froth. No detector has directly resolved a Planck-sized grain. These are attempts to describe what might happen where our best current theories overlap and strain. At ordinary scales, space-time looks smooth because any tiny quantum structure would be averaged over an enormous number of microscopic features. This is familiar from many areas of physics. Air feels like a continuous fluid when wind moves across your face, though it is made of molecules. A beach looks like a smooth line from far away, though it becomes grains when you kneel down. A digital photograph can look continuous until you zoom in enough to see pixels. But space-time may be more subtle than any of those examples because it is not simply an object inside space. It is the structure by which space itself is defined. If it has a grain, the grain is not located in space in the ordinary way. It is the grain of location itself. That is a difficult idea, so let us approach it from another angle. Imagine trying to draw a perfectly straight line on paper. Up close, the line has thickness, rough edges, and ink soaking into fibers. The straightness was an approximation that worked at the scale of your eyes. Now imagine space-time geometry as the line. General relativity draws smooth curves and paths. It treats space-time as continuous. Perhaps that is like viewing the ink from far away. At the smallest scale, the smooth curve may not exist as a clean object. The underlying structure may be rough, probabilistic, and relational. The path of a particle, the distance between events, even the meaning of before and after may become less definite. This matters for singularities. In general relativity, singularities appear in places such as the centers of black holes and the beginning of the universe in simple models. A singularity is not just a very dense object. It is a sign that the theory has reached a place where its own description breaks down. Curvature becomes extreme. Quantities that should be finite become unmanageable. Many physicists suspect that quantum gravity will remove or replace singularities, just as quantum physics resolved problems in older theories of atoms. If space-time becomes quantum at small scales, then perhaps the infinite sharpness of a singularity is smoothed, bounced, avoided, or transformed into something else. The early universe is another place where quantum foam may matter. If we trace cosmic expansion backward, the universe becomes hotter, denser, and smaller. Eventually we reach conditions where general relativity alone is not enough. Quantum gravity should become relevant. The earliest moments may not be describable as a smooth space-time expanding from an infinitely small point. Instead, there may have been a quantum gravitational phase where space-time itself did not yet have the familiar form we know. Asking what happened before that becomes tricky, because before assumes time already exists in the usual way. If time itself emerged from a deeper state, then the question may need to be rewritten. This is where language starts to struggle. We ask what space-time is made of, but made of usually means smaller things arranged in space over time. If space and time are the very things under investigation, ordinary making may not apply. Space-time may not be made of parts the way a wall is made of bricks. It may be emergent from relationships, from quantum states, from information, from causal order, or from something not yet named clearly. The smallest possible distance may not be a tiny length sitting at the bottom of a stack. It may be the point at which length stops being the right concept. That can feel frustrating. We like answers with handles on them. We like to say this is made of that. Wood is made of cells. Cells are made of molecules. Molecules are made of atoms. Atoms are made of smaller particles, then fields, then perhaps something deeper. But space-time resists this simple ladder because every rung of the ladder assumes some notion of place and sequence. To go beneath space-time, we may need a description that does not begin with place and sequence at all. That is why the problem is so hard. It is not just another hidden layer inside the familiar world. It may be the hidden origin of familiarity itself. Still, the idea of a smallest meaningful scale is not pure speculation without reason. It arises because quantum physics and gravity each impose limits. Quantum physics prevents unlimited precision. Gravity responds to energy. Put them together, and the attempt to define arbitrarily tiny regions becomes unstable. The Planck scale marks this meeting. It is not a proven wall, but it is a strong clue. If nature has a place where smooth space-time gives way to something deeper, that is where we expect the clue to point. Some physicists hope that black holes may serve as magnifying glasses for quantum gravity. A black hole contains extreme gravity and has a horizon that links geometry, thermodynamics, and quantum fields. The discovery that black holes have entropy was a major clue that space-time and information are connected. Entropy usually counts possible microscopic arrangements. If a black hole has entropy, one naturally asks what microscopic arrangements it is counting. Are these arrangements states of space-time itself? Are they quantum gravitational degrees of freedom? Are they encoded on the horizon? Questions like these suggest that space-time may have microscopic structure, even if we cannot yet see it directly. This also leads to the holographic idea, which says in certain settings the information inside a region of space can be described by information on its boundary. That does not mean the everyday world is a fake projection in the simple science fiction sense. It means that gravity may organize information in ways very different from ordinary field theory without gravity. The amount of information a region can contain may be tied not to its volume in the usual way, but to the area of its boundary. Black holes taught physicists to take this seriously. Once again, space-time begins to look less like a passive container, and more like a structure connected with information. The quantum foam picture also raises questions about time. If space becomes uncertain at tiny scales, time may as well. We're used to imagining time as a smooth parameter that keeps flowing while everything else fluctuates. But in quantum gravity, time itself is part of space-time geometry. It cannot remain completely outside the uncertainty. At very small scales, the distinction between earlier and later may become blurred in ways we do not yet know how to picture. This does not mean your alarm clock is secretly uncertain in any useful way tomorrow morning. At human scales, time remains stable enough to be deeply annoying when it rings. But at the Planck scale, the ordinary smooth flow of time may be an approximation. The word foam helps because it suggests instability without demanding a precise picture. But perhaps someday it will be replaced by something better. Scientific images often begin as rough guides and later become outdated. The atom was once pictured like a tiny solar system. That picture helped learners for a while but failed at deeper levels. Space-time foam may be similar. It may capture the intuition that smooth geometry breaks down, while the final theory describes something less frothy and more mathematical, perhaps networks, states, histories, or information patterns. The metaphor may be a lantern rather than a map. For now, what matters is the lesson. Smooth space-time is not guaranteed all the way down. General relativity tells us how space-time behaves when it can be treated as continuous. Quantum physics tells us that the microscopic world refuses perfect sharpness. At their intersection, The smallest distances may not simply be smaller versions of ordinary distances. They may mark a transition to a deeper kind of reality. This is a strange but useful humility. We can measure enormous cosmic distances, watch galaxies bend light, detect gravitational waves from black holes, and build clocks so precise they notice the difference between heights. Yet when we ask what happens at the smallest possible scale, the universe becomes quiet in a different way. It does not answer with a picture we can easily draw. It gives us hints. It gives us consistency problems. It gives us mathematical clues, black hole puzzles, and the stubborn success of theories that do not yet fit together. And so the smooth room around you, the steady distance from your bed to the wall, the calm ticking of time from one breath to the next, may all be large-scale appearances. Beneath them, space-time may have a hidden quantum texture. Not a texture you could touch, not a grain you could see, not a foam floating somewhere in the darkness, but a deep uncertainty in the geometry that makes somewhere meaningful in the first place. The universe may be smooth in the way a voice sounds smooth from across a room, even though up close it is made of countless vibrations. This thought carries us naturally toward the places where space-time is stretched most severely, where smooth geometry does not merely become tiny and uncertain, but extreme and dramatic. Black holes are the great testing grounds of these ideas. They are not just massive objects with strong gravity. They are regions where space-time forms boundaries, where time and space exchange roles in unsettling ways, where information appears to challenge our understanding, and where quantum effects near horizons suggest that the emptiest darkness may glow very faintly after all. After wandering down toward the smallest possible distances, where smooth geometry may become uncertain and restless, it is natural to turn toward the places where space-time is not merely subtle, but extreme. Black holes are often described as monsters, cosmic traps, or dark mouths in the sky, which is understandable because they do have a flair for drama. But if we slow down and look carefully, a black hole is not really a monster in the usual sense. It is a region where gravity has become so intense that space-time folds its rules into a form unlike anything we experience on Earth. It is less like a creature hiding in space, and more like a place where space and time themselves have been pushed to the edge of their known behaviour. The simplest way to begin is with escape. On Earth, if you throw a ball upward, it rises, slows, and falls back. Throw it faster, and it rises higher. Fire something fast enough, and it can escape Earth entirely. Rockets do this by reaching a speed that lets them climb away from Earth rather than return. Every object with gravity has an escape speed, the speed needed to get away from it. For Earth, that speed is large, but not impossible. For the Sun, it is much larger. Now imagine squeezing more and more mass into a smaller and smaller region. The gravity near the surface grows stronger. The escape speed rises. Eventually it reaches the speed of light. Since nothing known can travel faster than light through space, anything inside that boundary cannot send a signal outward. Not a rocket, not a stone, not a beam of light, not even the most determined complaint about the situation. That boundary is called the event horizon. It is one of the most important ideas in black hole physics, and also one of the easiest to misunderstand. The horizon is not a solid surface. If you crossed it, you would not hit a wall. There would be no metal gate, no warning sign, no cosmic employee saying, "Sorry, no exits beyond this point." It is a boundary in space-time, a point of no return. Outside the horizon, paths leading outward are still possible. Inside it, all future paths lead deeper in. The difference is not that your engines become weak, though they certainly would not help enough. The difference is that space-time itself has changed its structure. The future direction, the direction in which anything can continue, points inward. That is the truly strange part. In everyday life, space and time feel very different. You can choose to walk left, right, forward, or backward through space, at least until furniture or social expectations intervene. But you cannot choose to move backward in time. You move toward tomorrow whether you feel ambitious about it or not. Inside a black hole horizon, the inward direction becomes something like the future. Moving toward the centre is not simply a choice of direction in space. It is as unavoidable as moving toward next week. This is not because some force drags you in like a rope. It is because the geometry of space-time is arranged so that every possible future points that way. This makes black holes a kind of laboratory for the meaning of space-time. They show us that the geometry is not only flexible, but capable of forming boundaries that change what futures are available. An event horizon is not made of matter. It is not a shell of particles. It is a feature of causal structure, which means it separates events that can communicate with the outside universe from events that cannot. If something crosses the horizon, it can no longer send information back out to distant observers by ordinary means. The outside universe continues, but the crossed object has entered a region whose future is hidden. From far away, the approach to a black hole looks peculiar. Imagine watching a clock falling toward the horizon. According to the distant observer, the clock appears to slow down as it nears the boundary. Its light becomes stretched to longer wavelengths, fading and reddening. It never quite seems to cross the horizon in the distant observer's view, at least in the simple, idealized picture. It becomes dimmer, slower, and harder to see, like a farewell note written in ink that keeps dissolving. But from the point of view of the falling clock itself, nothing magical happens at the horizon if the black hole is large enough. The clock crosses in a finite time. It does not freeze. It does not feel the universe stop. This difference between viewpoints is not an illusion in the ordinary sense. It is a consequence of relativity. Time is not universal, and near a black hole the disagreement becomes dramatic. That is one of the reasons black holes are so useful for thinking about space-time. They force us to give up the idea of one single story told from one perfect perspective. The distant observer and the falling observer describe events differently, yet the theory accounts for both. This is not because reality has become sloppy. It is because space-time itself organizes time, distance, and causality in ways that depend on the path an observer follows. Near black holes, the flexibility of time is no longer a tiny correction for satellite clocks. It becomes part of the central drama. Black holes also bend light strongly. Light passing near a black hole can curve around it, sometimes looping in strange paths before escaping. A black hole can distort the appearance of objects behind it, acting like a gravitational lens. If it is surrounded by hot gas, that gas may glow fiercely as it spirals inward, heated by friction, magnetic fields, and violent motion. The black hole itself emits no light from within the horizon, but the region around it can be among the brightest places in the universe. This is one of the universe's more theatrical habits. The darkest objects can be surrounded by brilliant fire. The shadow of a black hole, captured by radio telescopes working together across Earth, is not a photograph of the horizon itself as though it were a surface. It is an image of light shaped by extreme gravity around the black hole. The dark central region appears because light from certain directions is swallowed or redirected, while the glowing material around it outlines the geometry. That image is powerful because it shows curved space-time not as a diagram, not as a metaphor, but as an observable effect in the sky. We are seeing light behave as though space and time have been sculpted by mass. But the horizon is only one edge. Deeper inside, classical general relativity predicts a singularity. This word means the theory has reached a place where its description breaks down. In the simplest non-rotating black hole, the singularity lies at the centre. In rotating black holes, the structure is more complicated. But in all cases, the singularity is not just a tiny dense object in the ordinary sense. It is a sign that the mathematics of smooth space-time has gone beyond what it can reliably describe. Curvature becomes extreme. The theory points towards something it cannot complete. This is where black holes connect to the question of quantum gravity. General relativity says black holes form naturally when enough mass collapses into a small enough region. Quantum physics says the world at small scales has uncertainty, fields, fluctuations, and discrete behavior in many contexts. Near the singularity, both gravity and quantum effects should matter. A complete theory of what spacetime is made of should tell us what replaces the singularities. Does the collapse end in some quantum gravitational core? Does spacetime bounce? Does the classical idea of inside and center fail? We do not yet know. The singularity is like a locked door at the end of general relativity's hallway, and every attempt at quantum gravity is partly an attempt to find the key or discover that the hallway itself has been drawn incorrectly. The horizon brings a second and perhaps even deeper puzzle. For a long time, black holes were thought to be perfectly black and rather simple from the outside. A black hole could be described by a few basic properties, such as its mass, rotation, and electric charge. Many details of whatever formed it seem to disappear behind the horizon. Whether a black hole formed from a collapsing star, a cloud of gas, or an encyclopedia collection of badly organized tax forms, the outside description could become almost the same. This simplicity is elegant, but also suspicious. Physics usually keeps careful track of information. If different arrangements of matter collapse into black holes that look identical from the outside, where did all the information go? The problem sharpened when Stephen Hawking showed that black holes should not be completely black once quantum fields are considered near the horizon. They should emit a faint thermal radiation. This radiation is now called Hawking radiation. For large black holes, it is incredibly weak, far colder than the cosmic background radiation around them. But in principle, it means black holes can lose energy and slowly evaporate. Very slowly for astrophysical black holes. So slowly that the times involved make the current age of the universe look like a brief cough. But the principle matters. If a black hole evaporates away completely, what happens to the information about what fell in? This is the black hole information problem, one of the great puzzles of modern theoretical physics. Quantum mechanics strongly suggests that information should not be destroyed. The evolution of a closed quantum system should preserve enough information that, in principle, the past can be reconstructed from the present. But Hawking's original calculations seem to suggest that black hole radiation is purely thermal, carrying no detailed information about what formed the black hole. If the black hole disappears and the radiation contains no information, then information has been lost. That would mean either quantum mechanics needs revision, or our understanding of black holes is incomplete, or both. Most physicists today suspect that information is not truly destroyed, but exactly how it escapes or is preserved remains subtle. The problem has led to some of the most important ideas about spacetime in recent decades. It has suggested that horizons are not just passive boundaries, they may encode information. It has connected gravity with thermodynamics, quantum entanglement, and the holographic principle. It has forced physicists to ask whether the inside of a black hole and the outside description are related in ways that our ordinary picture of space cannot easily capture. Black hole entropy is central here. Entropy is often understood as a measure of disorder, or as a count of possible microscopic states corresponding to the same large-scale appearance. A black hole has entropy proportional to the area of its horizon, not to the volume inside in the ordinary way one might expect. That is astonishing. It suggests that the number of hidden microscopic possibilities of a black hole is tied to the surface area of the horizon. This is one of the strongest clues that space-time and information are connected. If entropy counts microscopic states, what are the states of a black hole? What underlying ingredients are being counted? Are they states of quantum geometry? Are they degrees of freedom living on the horizon? Are they features of a deeper theory from which space-time emerges? This is where the holographic principle enters quietly but powerfully. It suggests that in a theory with gravity, the information contained in a region of space may be representable on its boundary. Not in the sense that the universe is a cheap illusion projected onto a wall, but in the precise sense that the deepest accounting of degrees of freedom may scale with boundary area rather than volume. Black holes made this idea difficult to ignore. They seem to store the maximum amount of information possible in a region, and that amount is tied to the horizon area. The edge of a black hole may be telling us something about the deep accounting rules of spacetime itself. The event horizon also creates a puzzle about locality. In ordinary physics, things are local. What happens here is influenced directly by nearby things, and signals cannot jump instantly across large distances. But black hole information seems to require that the inside and outside descriptions are related in a way that challenges simple locality. If information is not lost, then somehow the information about infalling matter must be reflected in the outgoing radiation or encoded in the horizon structure. But from the viewpoint of an infalling observer, nothing special may happen at the horizon. How can both be true? This tension has inspired ideas such as complementarity, where no single observer sees a contradiction, even though different descriptions appear incompatible if combined too naively. There are more dramatic proposals too. Some physicists have argued that horizons might be replaced by firewalls, violent regions that would destroy an infalling observer, contrary to the smooth crossing predicted by general relativity for large black holes. Others think that the interior of a black hole may be related to quantum entanglement in a way that preserves smooth spacetime. Some ideas connect wormholes and entanglement, suggesting that spacetime connections and quantum correlations may be two sides of a deeper relation. These proposals are debated, refined, challenged, and sometimes abandoned. That is how work at the edge of knowledge often looks from the inside. It is not a neat line of answers, but a careful struggle between principles that all seem too important to give up. Black holes also teach us that horizons are observer-dependent in interesting ways. An event horizon is a global feature of space-time. It depends on the whole future development of the geometry, not just on what a local observer measures at one point. That makes it unlike an ordinary surface. You could cross a horizon without noticing anything locally if the black hole is large and calm. There is no painted line on the floor of the universe. Yet from the perspective of causal communication, the horizon is absolutely meaningful. Once crossed, signals cannot escape to distant infinity. It is an edge not of material substance, but of possible influence. This is why horizons feel like edges of space-time, even though they are not edges in the simple sense of a cliff. Space-time continues inside the horizon, at least according to classical theory. But the horizon marks an edge of communication with the outside. It is an edge of what can be known by distant observers. It is an edge of return. Physics has always cared about what can be measured and communicated, so such an edge is not merely philosophical. It shapes the laws we can apply from outside. There are other horizons too. A rapidly accelerating observer in flat space-time can have a horizon, a boundary beyond which events cannot send signals that reach them. The expanding universe may have cosmological horizons, limiting what distant regions can ever influence us. Horizons are not only black hole features, they appear whenever spacetime structure limits causal contact. This suggests that horizons are deeply connected to the way spacetime, information, and observation fit together. Black holes are the most dramatic example, but perhaps not the only clue. The thermal behavior of horizons is especially striking. Black holes have temperature, they have entropy, they obey laws that resemble the laws of thermodynamics. This was unexpected. Thermodynamics began as the study of heat engines, steam, pressure, and energy flow. To find similar principles appearing in black holes, objects made from curved spacetime suggest a hidden connection. In ordinary matter, thermodynamics emerges from microscopic particles. Heat is the large-scale behavior of many tiny constituents. If black holes have thermodynamic properties, perhaps space-time itself also has microscopic constituents. Maybe gravity is, in some sense, a large-scale thermodynamic effect of deeper degrees of freedom. This line of thought is one of the most suggestive paths toward emergent space-time. If the curvature of space-time behaves partly like a thermodynamic system, then space-time geometry may not be fundamental. It may be like pressure, temperature, or elasticity, a large-scale description of many hidden microscopic states. We do not yet know the full story, but black holes keep pointing in that direction. Their horizons behave as if they know how to count, store, hide, and radiate information. That is not how a simple, empty geometric boundary was expected to behave. At the same time, black holes remain real astronomical objects, not just theoretical puzzles. We observe stars orbiting in visible massive centers. We detect X-rays from hot gas spiraling into compact dark regions. We have imaged black hole shadows. We have measured gravitational waves from black hole mergers, waves that match general relativity with remarkable accuracy. These observations confirm that black holes are not merely mathematical curiosities. They exist. The universe makes them, and it makes them often. Massive stars can collapse into them. Supermassive black holes sit in the centers of galaxies. The early universe may have produced smaller ones, though that remains an open area of study. They are part of cosmic life. When two black holes merge, the event is almost absurdly powerful. They spiral around each other, losing energy as gravitational waves. The waves carry away information about the masses, spins, and geometry of the system. Finally, the horizons merge, forming a new black hole that rings down like a struck bell, though the ringing is in space-time itself rather than air. Detectors on Earth can sense the passing waves as tiny changes in length, smaller than anything daily experience can make intuitive. From those changes, scientists reconstruct a collision that happened far away and long ago. It is one of the most beautiful confirmations that space-time is dynamic. It can be disturbed, and its disturbances can carry news across the universe. Yet even in these triumphs, the deepest questions remain. General relativity describes the outside of astrophysical black holes extremely well, but the horizon and interior connect to quantum theory in unresolved ways. Hawking radiation has not been directly observed from an astrophysical black hole because it's far too faint for large black holes, but the theoretical argument is powerful. The information problem remains active. The microscopic origin of black hole entropy remains one of the central tests for any theory of quantum gravity. A successful theory of what space-time is made of should explain black holes not only as curved geometry, but as quantum systems with countable internal states and consistent information behavior. This means black holes are not simply places where knowledge ends. They are places where shallow knowledge ends and deeper knowledge begins to press forward. They expose the limits of our current theories by forcing them into the same room. General relativity says horizon, curvature, singularity. Quantum theory says uncertainty, information, radiation. Thermodynamics says entropy, temperature, statistical counting. Black holes say all of you must be true together somehow. It is a demanding conversation, but a productive one. For the listener lying quietly somewhere on Earth, black holes may seem remote beyond imagining, and they are remote in distance mostly, but the lessons they teach reach into the room around you. They tell us that space-time is not a silent emptiness. It can form boundaries. It can hide regions from communication. It can carry entropy. It can ripple. It can be connected to information in ways we are only beginning to understand. The same space-time that lets a lamp sit beside a bed can, under extreme conditions, fold into a horizon from which light cannot return. The ordinary and the extreme are not separate universes. They are different expressions of the same underlying structure. A black hole is therefore less like a hole in space, and more like a statement about space-time. It says that geometry can become destiny. It says that time and space can trade their familiar roles. It says that boundaries without material surfaces can be physically real. It says that information may be woven into horizons. It says that the smooth fabric of general relativity and the restless world of quantum fields must eventually be understood together. And this returns us to the central question. If a horizon has entropy, what microscopic states does that entropy count? If black holes radiate, how does information survive? If space-time can form edges of communication, are those edges built from deeper quantum relationships? If geometry behaves like thermodynamics, could gravity itself be an emergent effect rather than a fundamental force? Black holes do not answer these questions simply. They make them impossible to avoid. So after standing near the horizon, at least safely in thought, we are led toward a possibility that changes the tone of the whole investigation. Perhaps space-time is not the deepest thing. Perhaps the smooth geometry that bends around stars and closes around black holes is a large-scale pattern, something that appears from underlying quantum structure the way fluid motion appears from molecules, or temperature appears from microscopic motion. To explore that possibility, we have to ask whether space-time could be emergent, not placed at the beginning of reality, but produced by something beneath it. That possibility is not as strange as it may first sound. We're already surrounded by things that are real, useful, measurable, and yet not fundamental in the deepest sense. Temperature is real. You can feel it in a warm mug, a cold window, or a blanket that has finally reached the proper level of evening cooperation. But temperature is not a tiny substance hidden inside matter. It is a large-scale description of the motion and arrangement of many smaller parts. A single molecule does not have temperature in the ordinary everyday way. Temperature appears when there are many molecules, many motions, many exchanges of energy, all averaged together into a property our bodies can feel and our instruments can measure. Pressure is similar. The pressure in a tire or in a sealed container is not caused by some separate pressure fluid. It comes from countless particles striking surfaces. At the large scale, pressure is smooth and practical. You can measure it, calculate it, rely on it, and be mildly annoyed when it is wrong in your bicycle tire. But underneath, it is the collective effect of many small events. The large-scale property emerges from microscopic behavior. This is the basic idea of emergence. Something can be real without being basic. Something can have laws of its own without being the final ingredient of the universe. A wave in the ocean is real, but it is not made of wave stuff. It is made of water moving in an organized way. A sound in the air is real, but it is not a little object flying from a speaker to your ear. It is a pattern of compression and rarefaction in air. A city is real, but it is not a single object in the same way a brick is. It is roads, buildings, people, systems, rules, habits, and routines arranged in a way that creates a larger structure. If one person leaves, the city remains. If one road is repaired, perhaps slowly and with impressive inconvenience, the city remains. The city is a pattern made of parts and relationships. So when physicists ask whether space-time could be emergent, they are asking whether space and time might be large-scale properties of something deeper, not illusions in the sense of being fake, and not imaginary in the sense of being optional, but emergent in the way temperature, pressure, waves, and solids are emergent. Space-time might be what a deeper system looks like when seen from far enough away, with enough pieces involved, and at energies low enough that the underlying structure becomes smooth. That is a careful idea, and it deserves careful handling. It does not mean that the room around you is not really there. It does not mean the distance from your bed to the door is a trick, or that tomorrow is only a rumour started by calendars. Space and time are real in every way that matters for ordinary life and for most of physics. You can walk across a room. Light takes time to reach your eyes. Clocks measure duration. Planets orbit. Gravitational waves pass through detectors. The question is not whether space-time works. It clearly works. The question is whether space-time is the deepest layer, or whether it is a smooth description that appears from something more basic. The reason this question has become serious is that our best theories leave clues pointing in that direction. General relativity treats space-time as a smooth, flexible geometry. It explains gravity with extraordinary success. Quantum physics treats matter and energy as fields, probabilities and excitations with uncertainty built in. It also tells us that the vacuum is not blank. When we try to bring these pictures together, space-time no longer seems safe as a fixed background. it becomes part of the problem. If gravity is geometry, and if gravity must be quantum, then geometry itself may need a quantum description. Once geometry becomes quantum, it may no longer be fundamental in the old smooth sense. Black holes make this suspicion stronger. They have entropy, and entropy usually points to hidden microscopic states. When steam has entropy, it is because the molecules can be arranged in many possible ways while giving the same overall pressure and temperature. When a hot object has entropy, it is because its microscopic constituents have many possible states. So when a black hole has entropy, physicists naturally ask what the microscopic states are. What is being counted? If black hole entropy is real, and all evidence says the idea is deeply meaningful, then perhaps space-time geometry has hidden degrees of freedom. The horizon may be a large-scale surface description of something quantum underneath. This is one of the strongest arguments that space-time might not be the final thing. A smooth, geometric horizon should not obviously behave like a hot object with entropy and temperature. Yet black holes do behave that way in the theory. They connect gravity, quantum fields, and thermodynamics. This is not a minor curiosity. It is a bright signpost. Thermodynamics usually means there is a deeper statistical story beneath the smooth, large-scale description. If space-time has thermodynamic behavior, perhaps space-time also has a microscopic story. Some physicists have pushed this idea very far. They suggest that gravity itself may be an emergent phenomenon, not a basic force. In this view, what we call gravitational attraction could arise from the tendency of microscopic degrees of freedom to arrange themselves in ways that increase entropy, or from the statistical behavior of underlying quantum information. This does not mean gravity is not real. It would be real the way pressure is real. A pressure wave can knock down a wall. An emergent thing can have very serious consequences. If gravity is emergent, then falling apples, orbiting moons, and black holes remain real. The explanation beneath them would change. A useful comparison is elasticity. A rubber band stretches because of molecular structure. At the everyday level, we describe it with elasticity, tension, and restoring force. Those are real properties. But they are not fundamental laws of isolated atoms. They emerge from the arrangement and interactions of many molecules. General relativity might be something like the elasticity theory of space-time, an extremely accurate large-scale description of how space-time bends and responds, while a deeper quantum theory explains what microscopic structure gives rise to that behavior. This is not proven. It is a possibility, but a serious one. Different approaches to quantum gravity explore it in different ways. Some imagine that space is built from discrete quantum chunks of geometry. Others imagine that space-time arises from causal relationships between events. Others connect geometry with quantum entanglement, the strange relationship by which parts of a quantum system can be linked so deeply that they cannot be fully described independently. In such ideas, distance may not be the starting point. Distance may be what strong and weak relationships look like when translated into the language of geometry. That last thought is especially important. We usually think that two things are related because they are near each other in space. You can touch a cup because it is nearby. You cannot touch the moon because it is far away, and also because that would be logistically difficult without a great deal of equipment. But in some emerging ideas, nearness itself may come from relationships. Two parts of a deeper quantum system might be strongly connected, and that strong connection may appear to us as spatial closeness. Weakly connected parts may appear far apart. Space would not be the container in which relationships happen. Space would be the large-scale map of relationships. This reverses our ordinary thinking. Instead of saying objects are close and therefore can interact easily, the deeper theory might say parts of reality are strongly related and therefore appear close. Geometry would be a translation of connection. It is a difficult idea because it asks us to imagine something that is not already laid out in space. Our minds want to put everything somewhere. Even when we imagine a deeper layer beneath space-time, we tend to imagine it as a hidden floor, under the floor, which is still a spatial picture. But if space itself is emergent, then the deeper layer may not be under anything in the ordinary sense. It may not have location as we understand it. Location may be what appears later. This is one of the hardest parts of emergent space-time. To explain what space comes from, we may need a theory that does not begin with space. To explain what time comes from, we may need a theory that does not assume a universal ticking background. That is like trying to write a recipe for flour without using the idea of ingredients, or giving directions to a place before the idea of direction exists. The language becomes strained because our words are built from the world we experience, and the world we experience already includes space and time. Still, physics has ways to work beyond intuition. It uses mathematical structures, consistency, predictions, and links between ideas that may not be easy to picture. One of the most productive clues has come from the study of certain theoretical universes where gravity inside a region can be described by a different theory without gravity on the boundary of that region. This is connected with the holographic principle. In these examples, space-time geometry seems to emerge from quantum information in a lower dimensional description. The details are technical, but the lesson is striking. A world with gravity and an extra spatial dimension can be equivalent, in certain cases, to a quantum theory without gravity living on its boundary. The geometry inside is not put in by hand in the usual way. It arises from the quantum structure of the boundary theory. This does not mean our universe has been fully explained this way. The known examples are not exact copies of the cosmos we inhabit, but they are powerful demonstrations that space-time emergence is not just loose speculation. In controlled theoretical settings, geometry can appear from quantum degrees of freedom. That gives physicists a laboratory for thought, a place to test how space, gravity, entanglement, and information might fit together. It is like finding a small working model of a mechanism, not yet the engine in your car, but enough to show that the design is possible. Entanglement appears again and again in this story. In ordinary quantum physics, entanglement means that the state of a combined system cannot be fully described by assigning independent states to its parts. The parts are connected in a way that is stronger than ordinary ignorance. In studies of emergent space-time, patterns of entanglement seem closely related to geometry. Change the entanglement, and the geometry can change. Reduce entanglement between two regions, and they may become less connected in the emergent space-time description. Increase or arrange entanglement differently, and the shape of space can respond. This suggests that space-time might be woven from quantum correlations. Woven is a metaphor, of course. There may be no literal threads. But the idea is that the connectedness of the quantum state may produce the connectedness of space. This is one of the reasons information has become so central to gravity. Information here does not mean gossip, documents, or a suspiciously long email marked urgent. It means the structure of possible states, correlations and distinctions in a physical system. It is about what can be known, how systems are related, and how many possible arrangements underlie a large-scale appearance. If space-time emerges from information, then geometry may be a kind of bookkeeping of relationships. Areas, distances, horizons, and volumes may reflect how information is organized. Black holes already point this way because their entropy depends on horizon area. Holographic ideas point this way because bulk geometry can be encoded on a boundary. Entanglement points this way because connections in quantum states seem able to build spatial connections. The clues are different, but they lean toward the same possibility. The fabric of space-time may be less like cloth and more like an organized pattern of quantum information. There is also a thermodynamic root to this idea. Some researchers have shown that Einstein's gravitational equations can be related to thermodynamic reasoning involving horizons, entropy, and heat flow. In this view, the equations of gravity may resemble equations of state, like those describing fluids. A fluid has pressure and temperature because of molecules underneath. If gravity behaves like an equation of state, then perhaps space-time has microscopic constituents underneath. Again, this does not settle the matter, but it gives a strong hint that geometry might be a large-scale description. The analogy with fluids is helpful but limited. Water molecules move inside space and time. If space-time itself is emergent, its ingredients cannot be imagined as little beads moving through pre-existing space in the same ordinary way. They would need some more basic kind of organization. Perhaps they are quantum states, algebraic relations, causal events, or something not yet captured by familiar words. We should not picture tiny gears floating in a smaller hidden space. That would only postpone the question. The deeper theory must explain where space comes from, not sneak it in through the back door wearing a fake moustache. Time may also be emergent. This possibility can feel even stranger than emergent space, because time is so central to experience. We feel change. We remember the past. We anticipate the future. But in some approaches to quantum gravity, the most fundamental description does not contain time in the ordinary way. Instead, time appears from correlations between parts of the universe, or from the way one subsystem can serve as a clock for another. Change is not measured against an external universal time. It is described relationally by how one part of the system varies with another. This is not as alien as it sounds. Even ordinary clocks are physical systems. A clock does not measure time from outside the universe. It changes in a regular way, and we compare other changes to it. The swing of a pendulum, the vibration of an atom, the rotation of Earth all serve as clocks because they provide reliable patterns. If the universe as a whole has no outside clock, then time may have to be understood through internal relationships. One part of the universe functions as a reference for another. At large scales, this relational structure becomes the time we know. The arrow of time may also be emergent. We experience time as flowing from past to future, partly because entropy increases. Memories form in one direction. Causes precede effects. The universe began in a low entropy condition, and structure has developed from there. If space-time itself emerges from a deeper quantum state, then the flow of time we experience may be tied to the growth of entanglement, the spreading of correlations, or thermodynamic behavior at large scales. Time would not be a river flowing through reality from the outside. It would be part of the way reality organizes change from within. These ideas are fascinating, but it is important not to make them sound more settled than they are. There is no final confirmed theory of emergent space-time. No experiment has yet shown directly that space is made from entanglement, or that time is only a large-scale correlation, or that gravity is purely thermodynamic. The evidence is suggestive, not conclusive. The work is active and difficult. Many ideas may turn out to be wrong or incomplete. Some may describe only special cases. Others may be hints of a deeper principle we have not yet named correctly. Science is careful this way. It allows imagination, but asks imagination to pay rent in evidence. Emergent space-time is attractive because it connects many puzzles: black hole entropy, holography, quantum information, the problem of time, and the search for quantum gravity. But attractiveness is not enough. A successful theory must reproduce general relativity where general relativity works. It must reproduce quantum field theory where quantum field theory works. It must explain black holes without destroying quantum mechanics. It must make new predictions, or at least provide new consistency that can be tested. That is a demanding list, as it should be. The universe is under no obligation to make its deepest layer easy to recognize. One reason the idea remains so compelling is that emergence has worked before. Solids, fluids, heat, sound, and materials all have large-scale laws that arise from microscopic behavior. At one time, heat was thought of almost like a substance. Later, it was understood through motion. At one time, atoms were theoretical. Later, they became experimentally unavoidable. Perhaps space-time is now in a similar position to heat before molecular theory was fully accepted. We can describe its large-scale behavior beautifully, but the microscopic explanation may still be hidden. If that is right, then general relativity may be like a theory of space-time elasticity. It tells us how the large-scale geometry responds to mass and energy, just as elasticity tells us how a material bends or stretches. But the material properties of rubber come from molecules. The properties of space-time might come from quantum information, entanglement, causal structure, or some deeper substrate. The comparison is imperfect, but useful. It allows us to see general relativity not as wrong, but as a high-level truth. A theory can be both accurate and emergent. The weather is real even though air molecules lie beneath it. This also changes how we think about what made of means. If space-time is emergent, it may not be made of smaller things located in space. It may be made of relations, correlations, or states whose large-scale behavior gives rise to location. A room is made of walls, floor, ceiling, and air all arranged in space. Space-time cannot be made that way if it is the origin of spatial arrangement. Its ingredients, if that word even applies, may be more like entries in a network of possible influence, or patterns in a quantum state. The deepest level may not look like a tiny version of the world. It may look like something from which looking and where only appear later. There is a calming lesson here, even though the idea is difficult. Reality does not have to match our first pictures to be understandable. Humans once pictured the Earth as still because that is how it feels. We pictured matter as solid because that is how tables feel. We pictured time as universal because that is how clocks seem in ordinary life. Each deeper theory did not erase experience. It explained why experience has the shape it does. Emergent space-time, if true, would do the same. It would not make the world vanish. It would explain why the world appears spacious, temporal, and geometric at the scales where we live. Think again of the room around you. The walls seem still, the air seems continuous, the floor seems solid, the seconds seem to pass evenly. All of that is true enough for life. But beneath the floor are atoms. Beneath atoms, fields. Beneath fields, perhaps deeper quantum structure. And beneath the smooth seconds, perhaps correlations that give time its meaning. You do not need to perceive those layers directly for them to support your experience. In fact, your experience depends on the stability of the large-scale world. If we directly felt every quantum fluctuation, every microscopic uncertainty, every hidden correlation, making a cup of tea would become an unreasonable act of theoretical physics. Thankfully, nature averages itself into tables, clocks, and mugs. The possibility of emergent space-time also changes the feeling of emptiness. Empty space may not be a blank absence. It may be a smooth phase of underlying quantum structure. Just as a calm lake surface hides molecular motion, empty space may hide microscopic degrees of freedom. The vacuum would not be nothing. It would be a state of the deeper system, one that looks like smooth space-time with quantum fields living in it. Add energy, change the state, curve the geometry, form a black hole, and the hidden structure reveals hints of itself through entropy, horizons, and radiation. Perhaps this is why space-time seems so different depending on how we approach it. To Newton it looked like a fixed background. To Einstein it became dynamic geometry. To quantum field theory it became the arena for fields. To black hole thermodynamics it became connected with entropy and information. To modern quantum gravity it may become emergent. Each view is not simply a replacement of the previous one. It is a deeper context. The older view remains useful within its proper range, while the newer view explains more. So could space-time be emergent? Yes, it could be. Many clues suggest that it might be, but we do not yet know the final answer. The evidence is strong enough to guide serious research, but not complete enough to close the case. The question remains open in the best scientific sense, not empty, not vague, but alive. It sits at the intersection of gravity, quantum mechanics, thermodynamics, and information. It asks what the universe is doing beneath distance, beneath duration, beneath the smooth geometry that carries planets and light. If space-time is emergent, then the deepest layer of reality may be less about things occupying places and more about relationships producing place. Less about moments flowing through a cosmic clock, and more about correlations producing time. Less about an empty stage and more about a vast organization of information whose large-scale pattern is the universe we inhabit. The next step is to follow that word information more carefully, because it appears again and again at the edges of space-time. In black hole horizons, in quantum entanglement, in holographic descriptions, and in the question of how the universe keeps track of what can happen, information begins to look less like a human idea and more like one of the basic ways reality holds itself together. Information is a familiar word, but it becomes surprisingly strange when physics takes it seriously. In everyday life, information means a message, a number, a sentence, a memory, a map, a password you wrote down somewhere and then very responsibly lost. It seems like something people use rather than something nature is made from. A book contains information. A phone sends information. A clock gives information. A friend saying I will be there soon gives information too, although the reliability of that particular information may vary depending on the friend. But in modern physics, information is not just a human convenience. It is increasingly treated as something physical, something tied to the deepest behavior of matter, energy, black holes, quantum systems, and perhaps space-time itself. To understand why this matters, we have to slow down and ask what information means in a physical sense. At its simplest, information is about distinction. It tells us which state something is in rather than another possible state. A light can be on or off. A coin can land heads or tails. A particle can be found here rather than there. A clock can read one time rather than another. A memory in your brain corresponds to one arrangement of physical activity rather than a different arrangement. Information is not floating in a ghostly realm outside matter. It must be stored in something physical. Ink on paper, magnetization on a drive, electrical activity in a brain, patterns of light in a fiber, or the quantum state of a particle. Wherever information appears, it has a physical carrier. This may sound obvious, but it was a major shift in thinking. For a long time, people treated information as abstract, like a note written about the world rather than part of the world. But physics began to show that information obeys physical rules. You cannot erase information without consequences. You cannot copy unknown quantum information perfectly. You cannot send information faster than light. You cannot ignore the way information is stored when thinking about heat, entropy, computation, and black holes. The universe does not treat information as a free extra. It keeps accounts. Entropy is one of the places where information first becomes unavoidable. In everyday language, entropy is often described as disorder, which is helpful but incomplete. A messy room has high entropy because there are many ways for it to be messy and relatively few ways for it to be perfectly tidy. A broken glass has high entropy compared with an intact glass because the shards can be arranged in countless ways. Beneath that idea is a question about microscopic possibilities. How many detailed arrangements could produce the same large-scale appearance? The more possibilities there are, the higher the entropy. Entropy is therefore connected with how much microscopic information is hidden from us when we describe a system only in broad terms. A cup of hot tea, for example, looks simple. It has a temperature, a volume, a colour, perhaps a level of milk that someone will judge far too strongly. But underneath that calm surface are enormous numbers of molecules moving, colliding, rotating, and exchanging energy. We do not track each one. We use temperature and pressure because they summarize the collective behavior. Entropy measures, in part, how many microscopic arrangements could underlie that summary. The large-scale world is smooth because we ignore almost all the details. That ignorance is not a personal failure. No one is expected to know the full molecular biography of a cup of tea. but physics can still count the possible hidden details, and that count is information. This connection between information and entropy becomes much more powerful in quantum physics. A quantum system is described not only by what we observe, but by a state containing possibilities and relationships. When systems interact, their states can become entangled. Entanglement means the parts are not fully independent. You cannot completely describe one part without referring to the larger whole. This is not ordinary hidden ignorance, like not knowing which drawer contains the spare batteries. It is a deeper kind of connection built into the quantum state itself. Entanglement is one of the most non-classical features of reality, and it has become central to the modern understanding of space-time. At first, entanglement seemed mostly like a strange feature of small particles. Two particles could share a quantum state so that measurements of one were correlated with measurements of the other, even across large distances. Einstein famously disliked the apparent weirdness of this. Experiments have since shown that quantum entanglement is real, though it cannot be used to send messages faster than light. It does not break relativity, but it does tell us that the structure of quantum reality is not the same as the structure of ordinary objects with pre-existing properties. The universe at the quantum level is not simply a collection of separate things carrying private labels. It is built from relationships. That word relationships brings us back to space-time. Space tells us how far apart things are. Time tells us how events are ordered. But if space-time is emergent, perhaps distance and order are themselves large-scale expressions of deeper relationships. Entanglement offers a possible clue. In some theoretical models, the pattern of entanglement in a quantum system is closely related to the shape of an emergent space-time. Stronger entanglement can correspond to closer connection. Changing entanglement can change geometry. Space may not be a container that comes first. It may be a way of representing how quantum information is organized. This is difficult to picture because our minds want to put relationships inside space. We imagine two things separated by a distance, then connected by a string, a signal, or a shared history. But emergent space-time asks us to consider the reverse. The connection may come first, and distance may be how that connection appears at large scales. It is like looking at a social network. Two people may live far apart geographically, but be closely connected through frequent communication, shared memories, and mutual influence. Another pair may live in the same building and never interact. Physical space and relational closeness are not the same in human life, of course, but the analogy helps soften the idea. In a deeper quantum structure, geometry might be a map of connection rather than the cause of connection. Black holes gave this idea real force. A black hole horizon has entropy, and that entropy is tied to the area of the horizon. This was shocking because ordinary systems usually store information in volume. A box of gas has more possible molecular arrangements when the box has more volume, but black holes seem to follow an area rule. The amount of information associated with a black hole scales with the surface of its horizon, not the space inside in the usual way. That discovery changed how physicists think about gravity. It suggested that the deepest information content of a region with gravity might be encoded on a boundary. This led to the holographic principle. The name can be misleading if it makes us imagine that the universe is a fake projection, like a cinema screen pretending to be three-dimensional. That is not the careful scientific meaning. The idea is that, in theories with gravity, the information needed to describe what happens inside a region may be represented on its boundary. A lower dimensional description can encode a higher dimensional gravitational world. The inside and the boundary are not two separate realities competing for attention. They may be two descriptions of the same physics. In certain mathematical settings, this idea becomes remarkably precise. A theory of gravity in a space-time region can be equivalent to a quantum theory without gravity on the boundary. The geometry of the gravitational world appears from the quantum information structure of the boundary theory. Again, these models are not exact copies of our universe, and we should not pretend they settle everything. but they show something extraordinary. Space-time can emerge from information in a controlled theoretical framework. Geometry can be built from patterns of quantum states. Gravity can be translated into a language of information. That is one reason modern physicists often say that space-time may be encoded. Encoded does not mean hidden in a computer somewhere, with the universe waiting for a password. It means that the same physical content can be represented in a form where space and gravity are not fundamental starting points. The distances and shapes we see in the gravitational description may correspond to relationships in a quantum informational description. A smooth interior space-time may be like a readable image created from a deeper code. There is another surprising idea here called quantum error correction. In ordinary computing, error correction protects information from damage. If one small part of a message is corrupted, the full message can still be recovered because the information is stored redundantly. Something similar appears in certain holographic models of space-time. Information about the interior can be distributed across the boundary in a way that protects it. This has led some researchers to think of space-time itself as having an error-correcting structure. The smoothness of space may be connected to the robustness of quantum information. That may sound extremely technical, but the broad idea is gentle enough. Imagine a memory that is not stored in one fragile location, but spread across many places. Damage one part and the whole can still survive. In some models, the geometry of space-time works like that. Local regions of the emergent space are encoded in shared patterns of information. The connectedness of space-time depends on how that information is distributed. If this is right, then space is not merely where information sits. Space is partly how information is organized. This changes the feeling of the universe. Instead of imagining reality as objects in a container, we begin to imagine it as a vast structure of possible states, correlations, boundaries, and transformations. Matter as field activity, gravity as geometry. Geometry may be information organized in a certain way. The vacuum may be a state of underlying degrees of freedom. Horizons may reveal the limits and storage rules of information. The universe becomes not a machine made of little hard pieces, but a layered informational structure whose large-scale appearance is stars, galaxies, rooms, clocks, and sleepy listeners. But we should be careful with the phrase made of information. It can easily become too vague. Information is not a mist or a substance. You cannot scoop it into a bowl. Physical information always belongs to physical states. So saying space-time is made of information is not the same as saying it is made of thoughts, numbers, or human knowledge. It means that the fundamental description may be about states and relationships rather than objects placed in pre-existing space. It means that what matters most at the deepest level may be how physical possibilities are distinguished, correlated, and transformed. There is also a difference between information we know and information the universe carries. Your knowledge of a system can increase or decrease, but the physical information in the system is not simply what is in your mind. If you forget where you placed your keys, the universe has not lost the information in the same way you have. The keys are still somewhere, likely in the least convenient possible location. In quantum theory, the question becomes deeper because information is tied to the evolution of states. A major principle is that the full quantum evolution preserves information, even if practical observers cannot recover it. This is why black hole information loss was so alarming. It seemed to challenge one of the central rules of quantum mechanics. If black holes preserve information after all, then the radiation they emit must somehow carry subtle correlations. At first, it may look thermal and featureless, like random heat, but the full pattern may contain the details needed to keep quantum information from being destroyed. This is not something one could easily read like a message in a newspaper. It would be unimaginably scrambled. Still, in principle, the information would remain. The black hole would be less like a shredder and more like the most extreme scrambler in nature, mixing information so thoroughly that recovery becomes practically impossible, but not fundamentally forbidden. Scrambling itself has become an important concept. Black holes appear to scramble information extremely efficiently. When something falls in, the information about it may become spread across the black hole degrees of freedom very quickly. This again suggests that black holes are not just gravitational traps. They are quantum information systems with remarkable properties. The horizon is not a simple surface. It is a place where gravity, thermodynamics, quantum mechanics, and information all meet. If spacetime has a hidden informational structure, black holes are where that structure shows its fingerprints. Quantum entanglement also plays a role in the smoothness of spacetime. In some ideas, the interior of a black hole, or even ordinary connected space, requires entanglement to hold it together. Reduce the entanglement between regions, and the geometry connecting them may weaken or separate. This is sometimes summarized in a slogan linking wormholes and entanglement, though the details are subtle and not settled as a description of our universe. The broad thought is that geometric connection may be deeply related to quantum correlation. Space may be stitched by entanglement, not with literal thread, but through the structure of the quantum state. This returns us to the title Thought, the universe as a woven story of information. Woven is a metaphor, but a useful one if we keep it grounded. The threads are not physical strings running through a background space. They are relationships, correlations, possible states, causal links, and constraints. The pattern they form may appear to us as space-time. Matter and energy are not separate decorations placed on top. They are excitations and structures within the same larger physical story. A star curves space-time because its energy and momentum contribute to geometry. A black hole stores entropy because its horizon reflects hidden degrees of freedom. Light travels along paths shaped by space-time, while space-time itself may emerge from quantum informational patterns. Each part of the story points to the others. Causality belongs in this weaving too. Information cannot be sent arbitrarily. Signals are limited by the structure of space-time. Light cones define what can influence what. In an emergent picture, causal relationships may be more fundamental than distance. A causal network could, in principle, give rise to space-time geometry. Events are related by which can affect which, and from a vast ordering of such relations, a smooth space-time might emerge. This is a different kind of making than building a wall from bricks. It is more like a pattern becoming a landscape. The arrow of time also fits into the informational view. We remember the past because physical records exist in the present. A footprint in sand, a photograph, a scar, a memory, a fossil, a line in a notebook, all are present arrangements that carry information about earlier events. The future does not have records yet. Entropy increases because information about precise microscopic states becomes spread into forms we cannot practically track. The world moves from special low entropy arrangements toward more typical high entropy arrangements. Our experience of time is tied to the creation, storage, and dispersal of information. Time is not just what clocks read, it is also the direction in which records accumulate and correlations spread. This does not mean time is only psychological. Clocks are physical systems, radioactive atoms decay, planets orbit, stars age. But our sense of a flowing history depends on information. Without records, the past would not be accessible. Without stable physical structures, memory could not exist. Without entropy, the difference between past and future would lose much of its everyday meaning. The universe tells its story by leaving traces. And what are we in that story? We are not outside observers looking in from beyond space-time. We are physical systems inside it, made of fields, atoms, cells, and memories. Our brains store information. Our senses gather information. Our bodies maintain order by exchanging energy with the environment. Every thought is a physical process. Every memory is a pattern. Every act of perception is a transformation of information from the world into the nervous system. We are not separate from the universe's informational fabric. We are one of the ways it becomes aware of its own patterns, though perhaps still confused about where the charging cable went. There is humility in this. The universe is not information because humans describe it. Rather, humans can describe it because the universe has stable patterns that can be represented, stored, and compared. Science itself is an information process. We observe, record, test, correct, compress, and communicate. A law of physics is a compact description of many possible events. It is a way of recognizing order. When we say space-time curves around mass, or particles or excitations of fields or black holes have entropy, we are finding patterns in the vast informational behavior of reality. Still, information alone is not a final bedtime answer. It does not magically solve every problem. We do not yet know the complete theory that explains space-time from first principles. We do not know exactly what the microscopic degrees of freedom of space-time are, if that is the right phrase. We do not know whether our universe is holographic in the same precise way as certain theoretical models. We do not know exactly how the smooth geometry of general relativity emerges from quantum states in our cosmos. The word information points toward a deep organizing principle, but the full map is unfinished. That unfinished quality is part of the beauty. The story of space-time has already changed several times. Space and time were once separate absolutes. Then they became a unified geometry. Then geometry became dynamic gravity. Then empty space became a vacuum filled with quantum fields. Then black holes revealed that horizons have entropy and temperature. Now quantum information appears to be one of the clues to how space-time might arise. Each step does not close the mystery completely. It makes the mystery sharper. So what is space-time really made of? The most honest answer is that we do not yet know in a final way, but we have learned what the answer cannot be if it is to respect everything physics has discovered. Space-time is not simply empty nothing. It is not merely a passive stage. It is not separate from time, matter, energy, gravity, and information in the simple way older pictures suggested. It bends, ripples, expands, forms horizons, shapes clocks, responds to energy, and may emerge from quantum relationships. If it is made of something, that something may not be material in the everyday sense. It may be made of quantum states and correlations. It may be made of causal order. It may be made of entanglement and information, or those may be different names for a deeper structure still waiting to be understood. Perhaps the safest image is not a fabric in the ordinary cloth sense, but a pattern. A pattern can be real. A song is a pattern in sound. A wave is a pattern in water. A memory is a pattern in the brain. A living body is a pattern maintained through matter and energy. Space-time may be the great pattern through which the universe becomes extended, ordered, and knowable. We move through it, measure it, age within it, and look across it towards stars whose light began travelling long before we were here to see it. At the deepest level, that pattern may be informational, relational, and quantum. And now, as this quiet journey reaches its resting place, notice the ordinary space-time around you again. The distance from your hand to the blanket. The time between one breath and the next. The soft darkness behind your eyelids if they are beginning to close. None of that feels like quantum information. It feels like a room, a body, a moment. That is the gift of emergence, if emergence is part of the answer. The deeper layers do not need to announce themselves constantly. They gather into a world stable enough for sleep, thought, warmth, and wonder. Somewhere far away, black holes are turning information into one of the hardest puzzles physics has ever faced. Somewhere between galaxies, space-time is expanding. Somewhere at scales too small to picture, fields are never perfectly still. And here, in this quiet moment, you are part of the same story. Not outside it, not merely watching it, but woven into it by every atom, every memory, every second of your path through space-time. So, wherever you're listening from tonight, whatever time your clock happens to show, take a slow breath and let the question remain open without needing to chase it. The universe may be made from fields, geometry, information, or something deeper than all our current words, but for now it has made this moment too. It has made the room around you, the darkness beyond the window, the stars beyond the darkness, and the gentle sense of being here. If this journey has brought you a little calm, a little curiosity, or simply a softer place for your thoughts to land, I would be grateful if you liked the video, subscribed, or shared this quiet space with someone else who enjoys science at a slower pace. Spacetime may not be what it first seems. It may be flexible, quantum, informational, and emergent. It may be less like a stage and more like the deep order that lets stages, actors, clocks, and stories exist at all. And as you drift toward rest, there is no need to solve it completely. Let the universe keep some of its secrets for another night. For now, you're here, carried gently along your own path through the woven story, with space around you, time beneath your thoughts, and the quiet mystery of reality holding everything together.